Last class, we started talking about different kind of data structures we could have inside of our database system. And we spent the entire lecture talking about hash tables. And we talked about how hash table, or data structures in general, but especially hash tables, can be used in a variety of places inside the database system, like using it for internal metadata, actually storing the underlying tables in our database, and also temporary data structures, like building a hash table to do a join. So for the first three uses of data structures, for a lot of these cases, the hash table is going to be good enough, right? Think of it like internal to the system. It's not very often you're going to need to be able to do range queries. Most of the time, you want to say, go give me a single key and give me, for given key, give me the value. And you're doing point query lookups. So the thing we want to talk about now, though, is table indexes. And this is where we may want to actually run queries that want to do range scans, and therefore hash tables are going to be insufficient for us because because you can only do single key lookups. So everyone here should be roughly aware of what a table index is, but I just want to provide sort of a more formal definition so that we have a basic understanding going throughout the rest of the lecture what we're talking about. So a table index is essentially a replica of some subset of attributes in our tables, and that we're storing in a more efficient manner that allows us to do efficient lookups to find the thing that we're looking for. So, in the worst case scenario, if we want to find a particular key in our table, we just do a sequential scan for that. But the idea of putting it into a table index, we would have this auxiliary data structure that we can traverse or do a lookup into and find exactly what we want more quickly than having to do a sequential scan. So the key thing to point out here is that the index is going to be a replica of the table. So that means that it has to be synchronized with the table. Meaning if we modify a tuple in our table, we want that change to be reflected in our index. Because we don't want any false negatives or false positives. We don't want to add something to our table, not put it in our index, and then we do a lookup to find that tuple, and it's not in our index, and come back with a negative result, right? So the database system is what's going to be responsible for maintaining these indexes and keeping them completely synchronized with the underlying table. And this is completely transparent to you as the application programmer. I don't know when I insert, I don't have to say, oh, insert in this table, and oh, by the way, update these other indexes. The database system, at least at a SQL database system, would see the insert query and know that not only do I need to update the table, I also have to update any indexes I have on that table. So there's this trade-off now in our system between having lots of indexes to make queries go faster and then the cost of maintaining them. And we'll see this as we go along today, and we saw this actually with hash tables last time, right? Inserting something into an index sometimes will be really fast and sometimes could be really expensive, depending on whether, wherever we want to insert a given key, there's something already there or not. So again, when we have a query show up, the database system is responsible for figuring out what's the most efficient access method for me to use, for the system to use, to answer the result of your query. And again, this is transparent to you as the application programmer. I just write my select statement. I don't specify normally, in some cases you can, I don't specify normally exactly what index I want to use. The database system can figure that out for me. And again, going back to the very first lecture, this is one of the benefits or the advantages of the relational model and a declarative language like SQL. If I now, in my table, I write a bunch of queries in my application, and then later on I decide to add the index, I don't have to go back and rewrite my SQL to now use that index. The database system can figure that automatically for me, in theory. It doesn't always get it right. So this particular step of actually taking a query and figuring out what indexes to use, this falls under the umbrella of query optimization, which is a super hard problem. We'll cover this after the midterm. But this sort of thing, it's like an optimization problem to decide what's the best way to execute a given query amongst all these different choices I have. So we'll cover that later on in the semester, but for now, just assume that we know what index we want to pick when we do lookups. So, of course, there's now, as in always in computer science and databases, there's this trade-off between doing one thing a lot versus doing it not at all. So if you have a lot of indexes, that'll make your queries certainly go faster to do lookups on them, but now you have this additional cost of having to store those indexes and actually maintain them. Right, so again, indexes are going to take up pages. We're going to store that in our buffer pool. We'll have to write that out to disk. So that takes up space. But then now, as I said, when I do updates to my tables, I have to then also update all my indexes to reflect those changes. So if my table has 1,000 indexes, which would, in practice, people do that kind of stuff. If I now do an insert, I have to do 1,000 updates to all those indexes. And my update operation or insert operation isn't considered done until I've modified all my indexes, because they have to be always synchronized. So again, we're not really going to discuss how you decide what indexes to pick, but this is another hard problem in databases as well. Right? They have tools to do recommendations for you to decide what indexes you want to pick, or you pay a lot of money for human DBAs to do this for you. All right, so the things we're going to talk about today is just an overview of what a B+ tree is, and then we'll spend some time discussing what are the implementation details we have to be concerned of when we build out our index, and then we'll finish up talking about some additional optimizations that real systems actually do to actually make this thing be useful in practice. Okay. So the first thing we need to address is this what is a B+ tree and how does that relate to a B tree? So this is sort of the downside in databases, is that a lot of times the same word is used to reflect different things, and it can be quite confusing for someone trying to get started to understand what's the actual difference between these things. So first of all, there's sort of this class of data structures called B trees. And then within that, there is a specific data structure that is a B tree. So oftentimes people use the B+ tree and B tree interchangeably. But if you go back to the literature back in the 1970s, these were actually distinct data structures. And Wikipedia has them as distinct data structures today. So the first B tree came out in 1971. Then the B plus tree came out 2 years later in 1973. There's no paper that describes what the B+ tree is. There's a 1979 survey paper that says, here's all the B plus tree or B trees that are out there. And oh, by the way, IBM invented the B+ tree in 1973. And supposedly there's a tech report that describes this, but you can't easily find it on the internet. And then in the 70s and 80s, there's a bunch of these other ones that are variants on this. The B* tree is a variant on the B tree. And then actually the B-link tree came out in 1981. And actually this was invented here at CMU. This is the paper that describes it. So this was written by Phil Lehman. That dude still works here. He's in the dean's office. So if you love this lecture, you can go talk to him. He loves, every time I see him, I always say like, oh, we discussed the B-link tree in my class. And he's like, oh, that paper's so right? So 40 years later, it's still around. So the reason why I showed these other trees is because we're going to focus on the B+ tree, but we're not going to, in a modern system, we're not going to use it exactly the way it's described in like the 1970s. We're actually going to borrow bits and pieces from all these other trees that existed before, but now we're just going to call that the B+ tree. And again, a lot of times you'll see in database systems, they'll say we're using a B tree. I can almost guarantee you, or at least I've yet to see a system where they say they're using a B tree and it's not really actually a B+ tree. Like if you go look at the Postgres source code or Postgres documentation, they talk about using a B tree, but from as much as I can tell looking at what it's actually doing, it's really a B+ tree. So again, these words are used interchangeably. I'll try to say always B+ tree. I'll briefly mention what a B tree is later on, but in practice, this is what we care about. This is what we want to use in our system. Okay, so a B+ tree is a self-balancing tree data structure. So the B in B+ tree or B tree means balanced. And the idea is that it's going to keep data we insert into our data structures in sorted order. And that's going to allow us to do efficient searches, sequential scans along the leaf nodes, insertions and deletions. And we can do all this in log n. Again, contrasting this with the hash table in the best case scenario was O1. Worst case scenario was ON. In a B+ tree, because it's balanced, it's always going to be log n. And that means essentially no matter the distance from the root to any key in a leaf node is always log n, no matter how many times we delete and insert and change things around. So the B+ tree came out in the 1970s because they were trying to build a data structure that would make it efficient to do index lookups on hardware where the disk was super slow and memory was limited. So the B+ tree has this nice advantage compared to like a B tree, is that you can just scan along the leaf nodes after you traverse to the bottom, and you'll read everything in sequential order, or doing sequential scan along them. You never have to go back up, in general. Again, even though this was designed in the 1970s, it's still widely used today. And actually, even for faster disks and for in-memory databases where there is no disk, the B+ tree actually outperforms a lot of things. And it's still very, very useful. So this is the original paper. This is one that everyone cites, the ubiquitous B tree from 1979. And it's here in this paper they describe, or they mention that, oh yeah, there's this thing called the B+ tree from IBM, and it came out in 1973. And this is what normally people cite when you want to cite a paper for the B+ tree. So what are the properties we're going to have in a B+ tree? So it's considered an n-way search tree, meaning we can, within every node in our tree, it can have m different paths to other nodes, or up to m paths, not always exactly m. Again, it's perfectly balanced. We're going to the data structure maintains the balance over time as you modify the tree. And so by balance, I mean that, again, the distance from one leaf node or any leaf node to the root is always going to be log n. It's always going to be the same. The other thing is we have to do is that we have to maintain this guarantee that each node is at least half full. So again, for the number of keys I can have in my node, I have to have more than half minus 1, half the number of paths in my tree, and then I have to have less than n minus 1. So n minus 1 would be a completely full node. So I always have to be at least half full. And then we'll see this when we start doing deletes. If I'm not, then I have to start moving data around so that my node is half full. And again, that's how they're going to guarantee this first one, that the distance is always the same. And then the simple one is that every inner node, which I'll describe in the next slide, if you have k keys stored in your node, again, you can have up to n minus 1. If you have k keys, you're going to have k plus 1 non-null children. You have k paths or pointers to k plus 1 paths or pointers to children below. Actually, quick show of hands, who here has seen a B+ tree before? Very few. Good. Okay, good. Again, this is the best data structure for databases, so this is why you're here. All right, so this is the basic B+ tree. All right, and the layout is that, again, along the bottom we have our leaf nodes, and then any node that's not a leaf node is considered an inner node. Now this tree has a height of 2, meaning it has 2 levels. So the inner node is also the root node. Right? There's always going to be one node at the top because that's how you enter into the tree. And then down here in the leaf nodes, we're actually going to have sibling pointers. So this is something that came from the B-link tree. So any inner node won't have sibling pointers, but any leaf node will. So now I can traverse to the bottom and scan along, and in any direction that I want to keep finding my neighbors, getting more data. So in the inner nodes, it's going to be this combination of keys and pointers. And so for the inner nodes, the pointer is always going to be to another node, or null if there's nothing there. And then the key is just the whatever attributes we're building our index on, whatever we're trying to store in this. And then these keys are then used to determine which path you should go down as you start doing a search for a given key. So in this case here, for this first key, 5. So the path to the left of it, going this direction, will be for any keys that are less than 5. And then for the one that comes after it would be implicitly anything less than 9 or greater than 5. So if I'm looking for something, a key that's less than 5, I would look at this and say, well, I'm looking for key 1. 1 is less than 5, so I go down this path, and now I find my leaf node, and I try to find the thing that I'm looking for. The leaf nodes, the key value pairs are just the key, the same way they are up above in the inner nodes, but then the value can differ. We'll see this in a second. It could either be a record ID to a tuple. It could be the actual tuple itself. It doesn't matter. It's just that the inner nodes have pointers. The leaf nodes have data. So again, this is just to repeat what I just said. But then the way to think about it in each node, it's an array of key value pairs. And you're using the keys to determine whether if you're in the leaf node, whether it's the thing you want, or if you're inner node, whether you go left or right. So in general, but not always, the keys are always in each node are always sorted in whatever the sorting order you want, the correlation you want for that node, right? So my example here, we just sorted in numerical order, and so that's going to allow us when we jump into a node, potentially, depending how it's implemented, we can do binary search in each node and try to find the thing that we're looking for, rather than just having to do a linear search. But sometimes linear search is good too. So the contents of what these values are in the leaf nodes can vary depending on the database system. again, could be record IDs, it could be the actual tuples themselves, and we'll see some examples in a second. All right, so let's actually look to see how these leaf nodes are actually implemented. So again, logically, you just sort of think of it like this: that you have this array, and you alternate with key value pairs, and this is typically how a lot of textbooks show what a B plus tree node looks like. And so the first thing to point is, since this is the leaf node, we have pointers at the end and the beginning of our array to our siblings, right? And this would be a node ID or page ID to allow us to go in either direction. Or if we're at the right side of the tree or the left side of the tree, it would just be null. But again, nobody actually stores, no real database system would store their internal key value arrays for a B plus tree leaf node like this. All right, and these are just key value pairs and these are just pointers. Typically, it's stored separately. So just like in our slotted pages, we would have a header that tells us metadata about what's in our page. So in this case here, we can say what level in the tree we are, essentially how many steps away from the root we are, how many free slots that we have remaining in our node, and then the previous and next pairs. And then now you see that we separated out the keys and the values. Let me take a guess why you'd want to do something like this. Yes?
That the whole B plus tree index can fit in one page, and then like that values can be in some other pages. He
said so that for a given page on a B plus tree node, that all the keys can fit in one page, and then the values can fit in another page. No, the keys and values are typically always stored in the same page. Yes?
Because they are not of the same size.
Exactly, so they're not of the same size, right? Furthermore, also too, if you're doing binary search on this, you want everything to fit in your CPU caches. So if you're back here with all this intermixed, in order to do binary search, I actually don't need the values at this point because I'm just trying to find the key that I want. So if you break it up, right, depending whether it's fixed length or variable length, you can jump through the keys much more efficiently. The values typically are always fixed length, right? Because they're either 32-bit or 64-bit record IDs. If they're tuple, that's a little more complicated. But in general, you always want to separate them. Right? And again, the way it works is just whatever offset you are in the key array corresponds to some offset in the value array. So if I find the key I'm looking for, I'm going to offset 4, then I know just to jump to offset 4 in the value array, and that finds the thing that I want. So as I already said, the values can vary depending on the system. Some systems will just store the record ID. This is probably the most common implementation that people use. This is what Postgres does. This is what all the other commercial database systems do. What's more complicated, and we can talk about next class, is what does it look like when you actually store the tuples in the data? So think about this. Instead of having a table heap with my tuples and then a B plus tree that stores my primary key, and therefore I have to keep them in sync, what if they were just merged together and the leaf nodes was actually the tables the tuples corresponding to our primary key. So now when I want to do a traversal to find a particular key or particular tuple, instead of having to do, in the first case, I traverse the index, get a record ID, then do a lookup in the page table and find that, and then go scan inside that block to find the tuple that I want. What if, as I do the traversal, when I land in the leaf node, there's already the data that I want? So MySQL and SQLite are probably the two famous ones that do this. In cases like Oracle and SQL Server, I think by default you get the one at the top, but you can tell it to do this at the bottom. You have to pass in special flags. So now I want to distinguish, since we understand the basics of a B plus tree, let's distinguish it from the original B tree. So the major difference is that in the original B tree, the values of stored in the index could be anywhere in the tree, meaning any inner node could also have a value to like a record ID or the actual tuple themselves. In the B plus tree, the values are only in the leaf nodes. So what are the implications of this? Well, one, in the B tree case, I don't have any duplicate keys because I can guarantee that each key will only appear once in my tree. In the B plus tree, because I have all those guideposts up above in the inner nodes, I'm basically duplicating keys. Furthermore, if I delete a key in a B plus tree, I would remove it from the leaf node, but I may not actually remove it from the inner nodes, depending whether I rebalance or not. Right? I may not have a path going down to it. Or sorry, if I delete it from the leaf node, I may keep it in the inner node because that's how I figure out what path to go down if I'm looking for other keys. So a B tree is going to be more economical in how much storage space it occupies because it's not duplicating keys. But the downside is going to be, and this is why that nobody ended up actually using this in a real system, is that it makes doing updates more expensive when you have multiple threads. Because now you could be moving things up and down, right? The tree, you know, I have an inner node, I modify something, and I may need to propagate a change below me and above me, and therefore I have to take latches on both directions, and that causes, as we'll see next class or next week, that can cause a lot of issues. In a B+ tree, I only make changes to the leaf nodes. I may have to propagate changes up above, but I only go in one direction. Yes?
Could you repeat what you said about duplicates in the B+ tree?
Yeah. So her question is, can I repeat what I said about duplicates in a B+ tree? So going back to this guy here. So this is a B+ tree. So the keys that I have that I'm trying to index are 1, 3, 6, 7, 9, 13. But if you look in the root node, I have a 5. 5 does not appear anywhere in the leaf node, meaning it probably got, in this case here, it had gotten inserted, and then it got deleted, but I didn't reshuffle, reorganize my tree, so I left it in the inner node. In a B tree, that'll never happen. Each key only appears once, and if it appears in the tree, then it appears in our key set. Does that make sense?
So you're leaving it there for like the searching purpose, but it's still like stored in the inner node?
A question or statement is, we leave it in here for searching purposes, and it's still stored physically in our nodes, but if I ask this tree, do you have key 5? I would say no, because I always have to go to the leaf node, then I try to find 5, and I'm not going to find it. So it'll still be there, but it's not actually a real key. Yep. Yes?
How do we deal with like inserts here if like we fill up one of the leaves?
Okay, so the question is, how do we deal with inserts when we fill up one of the leaves? We'll get that in a second. Yes, that's the next topic.
There won't be any duplicates in the leaf node?
His question is, will there not be any duplicates in the leaf nodes? Yes and no. So we'll see this in a second. So this would be considered a unique index, a unique tree, or unique keys. You can have keys that have non-unique values, and we have to handle that. We'll get to that in a sec as well. Okay. So I think the next topic is what he asked is how do we actually modify this? Absolutely, yes. Inserts. Okay. So the way we're going to do an insert is that we want to traverse down and figure out what leaf node we want to insert our new key into. So again, we use those guideposts on the inner nodes to decide whether we go left or right, depending on whether a key is less than or greater than what's stored in those key arrays. And then as we traverse down, eventually we will get to a leaf node. And then the leaf node is where we want to start a key. And so if the leaf node has space, then we just insert it in. For keeping the keys in sorted order, maybe we sort them. But there's enough space, we just insert it. If there's not enough space, then we have to split the node. We have to split the leaf node we just inserted into. And so the way we're going to do this is we're just going to take a halfway point in our key space, put all the keys that are less than the halfway point in one node, all the keys that were above that in another node, and then we update our parent node to now include that middle key, and then we have an additional pointer to the new node we just added. And now maybe happen to say, all right, well, this is actually a recursive thing, because if now my parent, as I try to insert the new key into the parent, if it doesn't have enough space, then we have to split it and then propagate the changes up above. So for one insert, we may have to reorganize the entire tree. And this is what I was saying before, just like in the hash table. If I insert into an index or through the hash table and then nothing's there, it's really fast. But if I had to scan a long time to find the slot I can go into, that can be more expensive. So sometimes we would insert into our tree, and it's going to be an expensive operation because we're reorganizing the entire data structure. And other times it'll be super fast and we don't have to worry about it. All right, so let's do a demo of this. So this is using rather than me doing animations in PowerPoint, this is from a professor at University of San Francisco that has a nice little web-based visualization we can use to. In theory, yes. Okay. And I'll add a type remotely. All right, so we'll do a max degree of 3. So that means that the max number of nodes we can have is 2, or sorry, keys in each node is 2, and it can have at most 3 paths going down. So we insert, can everyone see that? You insert 2. There's a visualization.
Question.
Yes?
Could you repeat again for the degree part?
So the degree says the number of paths coming out of it.
Yeah.
So degree of 3 means I have most 3 paths coming out of me if I'm an inner node,
Yeah.
and therefore I can store at most 2 keys. Because
And the reason is
again, so going back to what we showed in the very beginning. Question: why did I set it to 3, or why is it that way?
Why they're only going these 2 keys?
So again, this has a degree of 4. So it's always the number of passes is the number of keys plus 1. So I can store 1, 2, 3 keys, and this guy has to have a right pointer and a left pointer, right? And he has to have a right pointer, but that's shared, and there's the one at the end. So there's 4 paths coming out for 3 keys. Okay? All right, so is there a way to make this look better? Well, let's just keep going and see how it goes. So it's down over there. So I've only inserted, I think it's the demo. I've only inserted 2 keys, or 1 key. So right now it only has one entry in it. So now I'll insert, I have my mouse. We insert 6. Right? So again, it had space in that node, so I was able to insert it. And now I insert 4. And at this point, it has to split because it can only store 2 keys. So it split in half, put 2 over here, 4 and 6 in its own node, and then it took the middle key 4 and moved it up as the new root. And again, I have pointers going down to both of them. So now do insert in 5. Right, that can fit over there, accommodate just fine. So now I insert 5. What should happen? Right, it'll say, well, 5 is greater than 4. It's greater than equal to 4, so I no need to go down this direction. But I can only store 2 keys in this node, so I'm not going to have to split this guys and then rebalance everything. So hit enter. Right, 4 goes down there, puts 5 there. Right, it split the node. Put 4 in the middle over here, 5 and 6 over here, and then put 5 up because that was the middle key. And now we have pointers going to this node, the middle node here with 4, and that one 5. Right? So again, this is recursive. As I keep inserting more stuff, and I have to keep splitting, I have to keep splitting the changes up. Yes?
What if we have duplicate keys?
So he says, what if we have duplicate keys? So actually, I don't know whether this will matter. So I should insert 4.
But 2 4s.
Yeah, it did that. So there's different ways. Sorry, how do I? It's the resolution is jacked. F11, no. How do they do that? Sorry. There we go. Okay, sorry. So this is just sort of a toy diagram. In a real system, you could store 4 together and just maintain multiple entries for all the unique values of that you have the same key.
Yeah, and in this case, I mean, the worst case could not be login anymore because if we have all the keys to be 4, then the search could be login, could be all in. I mean.
So okay, your statement is if all my keys are the same, it's 4, 4, 4, 4, 4, 4. Then if I'm looking for an exact key value pair, then it's n because I do a sequential scan. Yes. So yeah, we can pop up Postgres. We can make a table that has 1 billion rows, and for one column we set the value to 1, and we can create every 1 billion row has the same value for that one column, and Postgres will let us build an index on that column. It's a stupid index to build because, as you said, they're all the same. So how do I say this? People will do stupid things. In general, don't be stupid and don't build indexes on things that you shouldn't use. Right? There's other types of indexes we'll see. So a hash table, there's other things like inverted indexes we could use that could be better if you had a lot of duplicate values. But think of like email addresses, or think of like phone numbers, or things that were like it's going to be vastly diverse. Then we won't really have that problem. Or a primary key, right? Primary key has to be unique. That would be great for this. Right. So again, is this clear? Okay. So let's go back. So to do deletes now, we have the opposite problem. Again, inserts, if we got too full, we run out of space and we have to do that split. If we delete, then it may be the case we end up being less than half full, which would violate the guarantees we have to have in our B+ tree. And then therefore we have to do the opposite of a split, which is a merge. So delete something, again, I just do my traversal, I go down to the tree, try to find the key that I want to delete. I'm always going to land in a leaf node. If my leaf node, after deleting that key, is still at least half full, then I'm done. I just remove it, maybe reorganize my sorted key arrays, but then that's it. But if I'm less than half full, then now I have to figure out how to get rebalanced. So the sort of one easy trick we could do is look at our siblings in other leaf nodes, and that's why we have those sibling pointers. We could look at them and try to steal one of their keys to make ourselves balanced. Right? As long as our sibling has the same parent as us, then it's okay for us to steal this because that doesn't require any rebalancing up above. So if we're not able to steal from our sibling, then we have to merge. So then we got to go take one of our siblings, combine all our keys together. That may actually end up being too full as well, but then we could split that as well. Oh, that's the same thing as just copying this. But we would merge, delete a key up above, and then now everything's balanced again. Again, just like in splits where like I may have to go propagate the change everywhere, when we merge and we're deleting keys, our parent now may become less than half full, and it has to merge, and therefore we have to maybe restructure the entire tree. All right, so let's go back and to our example here and do our demo. And of course, now I got to figure out how to get to the top right corner.
So we just maintain the siblings in the leaf nodes only?
Correct. His question is, do we maintain the siblings only in the leaf nodes? Yes. All right, so let's do delete 4. All right, let's start with delete 5. Let me scroll down and then hit enter so we can see this. Right, so it does a traversal. Oh, that was insert. Shit, sorry. Delete 5.
Insert again.
Yeah, that's insert, that's delete. Again, sorry for the low resolution. All right, so let's delete 5. In this case here, it should find both of them. I just only found one of them, so let's delete the other one. Goes down. That's fine. Again, at this point here, both these nodes are still more than half full, so that's fine. So now let's delete 4, and I suspect it will try to delete the one that's farther on that side. Go down, right, found that, deletes that. Again, that node is now half empty. And it has to have at least one. And because it was empty, it merged everything and decreased the height of the tree. Yes?
Only the leaf nodes have sibling pointers, then how would form a merge?
His question is, if only the leaf nodes have sibling pointers, then how do you actually do this merge? So the way it works, basically, think of a thread going down. It can maintain a stack of what nodes it visited as it goes down. And we're actually going to need to do this when we do what's called latch crabbing or coupling. As we go down, we take latches in case we need to reorganize everything. And so I have to know I have to hold latches up. When I go down somewhere, I have to hold the latch of my parent in case I need to reorganize whatever I'm doing down below. So I don't release it until I know I'm safe. So I know how I got there. Yes.
There are two siblings, so there are two siblings to the left and to the right. So
Yeah. His question is, if there's two siblings to the left or the right, which one do you choose? It depends, right? Typically, you choose the one that has the same parent as you. Actually, I think you have to, actually. But if you're like, if you were in the middle, yeah, these guys have the same parent. So you say you want to reorganize this, you could choose either left or right. It doesn't matter. Let's see what this one does. So if we delete 4, that should take it out of the middle. And then now I delete 2, and it's going to pick either left or right. Okay, actually, it can only have 1 or 2, so it went empty, and that deleted it. We can increase the degree of the tree, but like it doesn't matter. It'd still be correct. And so this one also, this diagram shows the sibling pointers going in one way. You can have it go in both directions. You have to do extra work to make that happen, but like you can do that. A lot of times, again, for simplicity, you could just have it go in one direction, but then you can't do order by in descending order and go the other direction if you want to do scans. Right, pretty straightforward. Of course, getting the details of the deletes and inserts, doing that split and merge is actually very difficult in practice. And we'll see in next week how to actually make sure that when we're reorganizing the tree, that we're thread safe and we don't have any integrity issues. All right, so in practice, the research shows that the typical fill factor for a real tree on real data is about 67 to 69%, meaning the amount of data storing in your nodes that's actually real is up to 67% of is actually useful data. So typical capacities you can have, when for the 8 kilobyte pages, with this number of pages at 4 levels, you can basically store 300,000 key value pairs, right? So you can index and get in log n time to any one of 300 million keys fairly quickly. And most of the data is again going to be stored on the leaf pages, as you would expect, right? Because as you add more keys, you start to fan out, and most of the data is going to be stored in those leaf nodes. All right, so let's talk about some other things you can do with these indexes. So there is this concept of this notion of what are called clustered indexes. And so I said in the beginning that the table heap for a database is unordered, meaning we can insert tuples into any page in any order. We don't have to follow the temporal order of how things got inserted. But there may be some times where we actually want to have the data sorted in a certain way, like for example, like the primary key. So these would be called clustered indexes. So you can define an index when you create a table. You can define what's called a clustered index, and the data system will guarantee that the physical layout of tuples on pages will match the order that they're sorted in the index. So this is useful for certain things like, if I'm doing a lot of lookups within exact ranges of the primary key, if I know my tuples are stored in the same order of that primary key, now when I traverse the leaf node, within a small number of pages, I can find all the data that I need. If I'm not sorted on the key I'm doing my lookup on, then every single record ID I could have could point to another page, and I could be doing a bunch of different random IOs to go read the data that I want. So not all database systems support this. Some database systems, you get this by default, like MySQL, by storing the tuples in the leaf nodes themselves. It is a clustered index. So it's guaranteed to have on the pages on disk, the tuples are sorted in the primary key order. In the case of MySQL, if you don't define a primary key, they'll make one for you, right? They'll have a synthetic like row ID or record ID that's transparent to you, but that's how they use to figure out where your tuple is actually located. In case of Postgres, we can do a demo next time, but they have clustered indexes. You can define one. You can say cluster my table on this index, but it won't actually maintain it in that order. Meaning it does the sorting once, stores it on disk, but then over time it can get out of order because it won't do it for you automatically. And when we talk about multi-version concurrent control, it'll become very clear why this is the case for them. So let's talk about how we can do some lookups on our B+ tree. So again, because things are in sorted order, we can do fast traversal to find the thing we're looking for. But one advantage you can do with a B+ tree that you can't do with a hash table is that you don't need to have the exact key in order to do a lookup. You can have actually some part of the key. So let's say a real simple example, I have an index on attribute ABC. So I can do lookups like this, where A equals 5 and B equals 3, where I don't have the C, but I have A and B. And I don't need to have the C, and I can still find the things that I'm looking for. You can't do that in a hash index because think what would happen. I would take this 5 and 3, try to hash them together without the C, and that's going to jump to some random location that's not what I'm looking for. You can also do queries where you only have maybe the middle guy, right? You don't have the prefix, you don't have the suffix, you just have the middle key. Again, you can't do that in a hash table. So not all database systems support this. Pretty much everyone supports the prefix one, where you have at least the keys in the order as they're defined for the index. Not everyone can do this middle one here. Actually, I think maybe only Oracle and SQL Server can do this. So let's look at a little more concrete example. So let's say we have an index that is defined on two columns or two attributes. So this would be called like a composite key. So instead of being on for one column, it's actually two columns combined. And the order of how we define our index will determine what kind of queries we can do on them. So again, if I'm trying to do a lookup on say to trying to find key AB, well, in that case, I have both attributes that I've defined in my key. So now I can just do a straight comparison of look at the first key and then look at the second key and then determine whether I want to go left and right. So in this case here, A is less than or equal to A and B is less than or equal to C. So I know to find the key that I'm looking for, I go down this path, do whatever search I want to do in my node, and then I can find the entry that I want. Let's say, though, now I want to do a prefix search where I only have the first element of my composite key, but not the second one. So again, I can just look at the first key, or first attribute of the key. A is less than or equal to A, so I know that the starting point for what I'm looking for has to be down in this direction, so I go down here. But now I'm going to do a sequential scan across my node and going across the leaves to find all the entry I want up until I reach a key that is less than or equal to my key A. So in this case, as soon as I find one that starts with B, I know my search is done, and there's not going to be anything else remaining in the leaf nodes that would satisfy my predicate. So this one, again, this one's pretty easy, or not easy, but a lot of data systems can support this one. The hard one is this, where you only have the last element and not the first one. So the way you actually end up implementing this is you try to figure out, at least in the top, in the root node, which portions of the tree do I need to look at? It could be something, that there's something could be there. So in this case here, I know that no matter what I have for the first value, it's always going to have to be less than C for the second attribute, the second value. So I don't need to look at this guy over here. I only need to look at these other ones. So essentially what you just do is you end up doing multiple index probes or multiple traversals and substituting different values for the thing that you don't have. So you would look at the top and say, well, I know I have an A, I have a B, and I have a C. Well, there's nothing for this C that I would find over here, so I can skip that. So let me now do a lookup in these guys, and I substitute the star with an A. And each one of those is a separate lookup. And then you combine them all together and produce the final result. So Oracle calls this skip scans. I don't know what other systems call them. Yes?
Like, for the one on the right, couldn't there be a DB? So, like, wouldn't that match? Like, how do you know you're not? Like, in this example, like, you know, but ahead of time. Because, like, it's greater than.
Yeah. Yes, you're right. That's wrong. But yes. So you would include that, but each one of those is a separate traversal. And you're just filling in the values. Whereas like in this one here, the main point I'm trying to make is like this one, like for this one and the first one, I had to do one traversal and then I found the thing I was looking for. This one is you have to probe down multiple times and you fill in the values. Thank you, I'll fix that. Okay. So let's get to the good stuff. So we know what a B plus tree is now. Let's talk about actually how you want to build it and make this thing actually useful. So there's this great book, which I think is free. At least if you Google it, it shows up free. I don't know whether that's true or not. There's a great book written a few years ago by Gertz Graffi, who's a famous database researcher. We'll talk about a lot of the stuff he's done for query optimization later on. But he wrote this book as like all the modern techniques and tweaks and optimizations you can do in a B plus tree in a real system. So we're going to cover some of these things. And actually, it's a really light read. And well, it was, and like it covers all the really important topics in a way that's easy to read. So we'll talk about how to handle different node sizes, how to do merging, how to handle variable length keys, the non-unique keys, what they asked about, and then inter-node search, how to do better searches inside the node. So in general, you can think of a node in our B plus tree as just like a page in our table, right? So the size of the node could be the same as a page size. In practice, though, it doesn't have to be, and depending on what kind of hardware we're storing our database on, we actually may want to have even larger page sizes or smaller node sizes or smaller node sizes. So it turns out the research shows that the slower the disk you have, that you're storing your index on, your tree on, the larger the node size you want. And, it should be obvious, right? For every disk I/O I do, I can read the node sequentially, all the pages for it, and that's going to be much faster than do a bunch of random I/O to different nodes if my node is a smaller size. So if you're on a spinning disk hard drive, you can have node sizes up to 1 megabyte. That's usually a good number. SSDs are roughly 10 kilobytes, which roughly corresponds to the node sizes or page sizes that real database systems use. But then if you're an in-memory database, you actually want to go low as 512 bytes. And so this is another good example where we talked about how in our buffer pool, we could have one buffer pool in our system for index pages and one buffer pool set for data pages, and we could set them to be different sizes. So I could set, if I'm on a slow spinning disk hard drive, I could have a buffer pool for my B plus G pages and have them be 1 megabyte, whereas my data pages, I'll keep them at 8 kilobytes or 16 kilobytes. The optimal size can also vary depending on what kind of operations or queries you're doing on it. So leaf node scans, where you're doing long sequential reads, those are typically better to have larger node sizes because I can do more sequential I/O. Whereas if I'm doing a lot of lookups, a lot of traversal, that's a lot of random I/O, so therefore I want to have smaller node sizes. So the next thing we can do is actually violate the very thing I said in the beginning about how we always have to merge anytime we're less than half full. And in the demo I did, it was sort of simple. It would do exactly that. But in practice, you may actually not want to do this immediately when you're less than half full. Because it's just like when we saw in the hash table when we did deletes with linear hashing at the end, I may compact something, I may merge something because I went less than half full, but then the very next operation inserts into that node, and now I have to just split all over again. So the merging operation is expensive. Splits are also expensive, but splits we have to do because we ran out of space in our node. But the merges, we can actually relax that requirement and not merge things right away. So it gets slightly unbalanced over time, and then in the background we can have like a garbage collector or something go through and do rebalancing. Or what's oftentimes the case, people just rebuild the entire tree from scratch, and that fixes all these issues. So a lot of times you see this in high-end commercial enterprise systems. They'll shut the database down over the weekend because they're going to rebuild all their indexes, and that's essentially what they're doing. They're rebalancing everything because it wasn't always merging correctly. Anytime you see like a bank says they're down at 3 a.m. on a Sunday in the morning, this is one of the things they're probably doing. All right, so now we want to talk about how we actually want to handle variable length keys. So again, everything I've shown so far, we assume that the key is a fixed length and the value is always fixed length. And in practice, the values will always be fixed length. So there's 4 different ways we can handle this. So the first approach is that rather than storing the key itself in the node, we just store a pointer to the actual attribute or the tuple where we can do a lookup to find what the key actually is. So again, if I have an attribute that's a variable length varchar, instead of storing that varchar in the node, I have its record ID. And then when I want to figure out whether the key I'm doing a lookup on matches that key that's stored in that B tree, I follow the record ID, go get the page, and go look at what the real value actually is. So this is obviously super slow. It's nice because we're storing less data because now we just store the pointer instead of the actual key in the node. But it's expensive to do that lookup, as we're traversing. People tried this in the 1980s for in-memory databases because memory was really expensive, but nobody actually does this anymore. Everybody stores the keys always whole in the node. The next you can do have variable length nodes. This is basically allows the size of a node can vary based on what's stored in it. But we said this is a bad idea because we want our page sizes to be always the same in our buffer pool and on disk, so we don't have to worry about doing this bin backing problem to decide how to find free space to put in what we want to store. So nobody does this one as well. The next approach is to do padding, where basically we look at what the attribute is that you're trying to index on, and we say that whatever the max size it could be, no matter what key you give us, we will pad it out with either null bits or zeros to make it always fit exactly our node size. So everything is always nicely aligned. So some systems actually do this. I think Postgres does this, and we can look at that next time. But again, it's a trade-off. I'm wasting space in order to store things. So this is why is also too, it's super important to make sure that you define your schema correctly. Like if I'm storing email addresses, which are maybe 32 characters or 50 characters, but I set the varchar size to be 1024, if I'm padding it out up to 1024, even though most of my emails aren't that big, then I'm wasting a lot of space. Yes?
What do you do if like you're just keeping strings in general here because you just define the maximum size of strings always, like it's just defined in the schema as opposed to like.
So for that, sorry, say it again. Sorry.
Just in general, like, because like these aren't like necessarily like C strings where they have to L in an L terminator to be like.
Correct.
Like you always define the length.
Yeah. So like when you call create table, you can define varchar and you define the length in it. You don't have to put it in. I don't. Different systems default to different things, but in practice, you always want to say this is the max size of what I actually can store, right? And then so varchar is supposed to be variable length. So even though say the max size can be 32. If you give it a 16 character string, it could, in theory, store that more compactly. Some systems do different things. Some systems actually, if you say it's a char, where it's always going to be that size and it's always padded out, they actually just store that as a varchar. So logically, you don't know, you don't care. Underneath the covers, they can do different things. And MySQL was always the worst offender. So if you say the max size of a string is like 16, and you give it a 32 character string, it'll store it. It just truncates it silently for you, right? So Postgres and other systems will throw an error, but the database system should enforce that correctly. Same thing for index. To build an index, we have to be told, here's the attributes in our tables you're indexing, so we know what their type is, we know what their max size is, and we can pad out as needed. All right, what's probably more common is to use an indirection map, where we'll store pointers for our keys inside of our sort of key array, but the pointers are just actually to offsets in our node themselves, rather than to some arbitrary page. So it would look like this. So we have the sort of key map. So again, this is sorted. These are just pointers or offsets to down here, but these are sorted based on the values of the keys. So to be very clear, the keys themselves, not the keys corresponding value, but the actual string that we're trying to store, right? And so just like in the slotted page layout for tuples, we're going to grow from the end to the beginning, and this side grows from the from beginning to the end. And at some point we get too full. Actually, I think this has to be fixed size, so we have to set the degree ahead of time. So, but if I don't run out of space for what I'm trying to store here, then I can have an overflow page that's chained to this. So again, this is just an offset to whatever the key is. So now if I'm doing binary search, as I'm jumping around this array, I jump down here to see what the actual key value is. So what's a really simple optimization we could do to make this go faster? In the back.
So is the sorted key map stored as a vector or a linked list? If it is stored in the linked list, then you can
His statement is it a statement or a question? Do we store this as an array or a linked list? It's always stored as an array.
But if you do some insertion or deletion to this key map, you can take all and
Okay, so his statement is, I'm storing this as an array or a vector. Vector is just a wrapper on an array. If I now do insertion or deletion, that's going to take on. Or yes, but again, like this is just within the node itself. So the size is not that big, right? So fan out of like maybe 32. So I have 32 elements I need to keep sorted. I can do that in cache. That's very fast. So
like when you are moving down, always you compare when you have to compare with different keys, you like compare that key first going to the pointer place and then compare.
Correct. Yeah. So say I'm doing binary search. So in this case, binary search is just just do linear search. So I just scan along, and I want to see does the key I'm looking for match what I have. So I have to follow this pointer, which again it's just an offset. It's in the same page. So it's going to be maybe 16 bits. I follow that offset to jump to where this is, and then I do my comparison. And if it doesn't match, then I jump back and do the same and jump down here. And so just like in slotted pages, where the tuples don't have to be sorted in the order as they're laid out in the page, in the same way they're sorted at the slot array. This variable length data at the down here can be in any order that it wants. I just know how to, I know how to jump to it based on this.
For non-leaf nodes also we do the same thing.
His question is, for non-leaf nodes, do you do the same thing? Yes. It's in. This is for variable length data in any node. So this is sort of a micro optimization. And going to disk is always the most expensive thing. But a really simple thing we could do is just recognize that since this is only 16 bits in general, I have a lot of space up here. So maybe I just take the first character of every string and just embed it inside up here. So now when I'm scanning along and trying to find the thing I'm looking for, if my key doesn't match exactly the first character, then I know I don't need to traverse down and find it. So again, this is all going to be in memory. This is like avoiding cache misses in making the binary search and making the search on this run faster. So again, this is a micro optimization. Avoiding disk is always the major thing that we care about in this course, but this is a really simple trick you can do to speed this up. Yes?
What if there are two persons whose names start with the same letter?
Again, so it's like, what if there's two persons that name start the same letter? Again, you'd have to, depending on what you're looking for, if you want to find exactly one, you find the first one and you're done. If you need to find anybody, you have to go to both of them, right? I mean, same way here, right? For this one here, I'd have to, if I'm trying to find, everyone's different here, but if there's like Paul and Prashant, who's my PhD student, I would scan down here, find Prashant, then actually go to the next one to make sure that that one doesn't have the same, doesn't have the same thing as well.
But this will work only if your sorting is based on the names. Like you can define sort functions also, right? Like which map the strings to certain numbers, and those are used.
Okay, so he's talking about collations. So so I'm showing lexicographical ordering, alphabetical ordering for this. There in high-end database systems, you can actually define arbitrary sort orders. Everything still works the same.
Then what will you store there?
You're talking about like dictionary codes. We're not even talking about that. I can have different, sorting based on whether it's Unicode or what language I'm using. For that one, you have to, again, the data system would know this is how the sort order is. So it would know what prefix if it wants to store up in here. Again, the high level idea is still the same. Yes.
I want to double check. So, like, if we have k plus 1 degree, that means we have at most k keys.
Correct.
And then when we want to explore something.
So let me repeat what he said. So he said, if you have k keys, you have at most k plus 1 pointers to other things.
And then you explore all the k keys to find out the potential one that you want to go through.
Not necessarily. For simplicity, yes. You just scan along the keys and do a linear search.
And then, so the time complexity should be like k times log n instead of log n.
And so his statement is that really the complexity should be k times log n.
Yeah.
Yes. That's a constant we can throw out. Because the log n is the maximum number of page IOs I have to do to traverse. That's always orders of magnitude faster than doing the cache line lookups here. Remember I said in the very beginning, here's the storage hierarchy. Anything above memory we don't care about. We can throw away. It's the disk IOs is the real killer, and we got to avoid that.
Won't we do binary search?
We'll get to that in a second. Okay. All right, so now to get to the other thing that people asked about is how we handle non-unique indexes. Well, this is the same thing we talked about in hash tables. There's two basic approaches. You can just duplicate the keys and be mindful, like in our example here, that duplicate key split over to another node. We have to be mindful that could occur and make sure we read everything we need to read. Or we just store a value list where we store the key once and we duplicate the value, or have a separate space in our node to store all the values for that given key. Right, so it looks like this. So if I duplicate the key, right, I just have the key multiple times, and again, it's just like before. The offset points down to wherever the value is, and if I insert a new one, then I insert it here and insert a new K1. I just insert it here and move everything over, and everything still works. The value list essentially just looks like this. I just store the key once, but then now I also have a pointer or an offset to somewhere else in the node where I have all the values that correspond to that given key. The first approach is more common. I don't know who actually does this one here. Yes?
Can you like assume that for like duplicate keys, that they'll always be the same node? Like for like bounding purposes, is it possible that they're
So her question is, can I assume for that duplicate keys will always be in the same node? No. So an example I showed from that demo, it actually moved it over as a sibling key. That's one way to do it. Other systems actually would have an overflow chain that would say, for that given leaf node, oh, by the way, here's some other pages or other nodes down below you that have have the keys that correspond to what you're actually storing up above.
So if you're searching for a key, would it like how would it know which key to follow if they're in different nodes?
The question is, if I'm searching for a given key, how would I know what key to follow? So going back to that example, if I'm looking for a greater than or equal to 4, I have to go down on this side and find the first entry point for 4. Then I keep scanning along the leaf nodes until I find something that's not equal to 4, and then I know I've seen everything. Again, the database system knows whether the keys are unique or not, so it knows whether it has to do that. So it knows that, oh, this is a primary key, or this is a unique index, so the thing I'm looking for should only appear once, and therefore I just get to the one leaf node that has what I want. If it's non-unique, then you have to account for that, and either, again, if it's just duplicated across leaf nodes, I scan along siblings. If it's an overflow, I just find the first leaf node and then scan down its chain. Yes?
So the size of key is not always the same. How about the values?
The question is the size of the key always the same, or the size of the key is not always the same, or the value is always the same. Again, I'll show this next class. If the value is just a record ID for a tuple, always the same. It's either 32 bits or 64 bits, depending on the system. If it's the actual tuple itself, like in MySQL, then you got to deal with overflows that way, and that's more complicated. We'll discuss that next class. All right, again, we've already discussed this briefly, but I'm going to show you that there's different ways to do searches within the node. Again, as I'm traversing the nodes, traversing the tree, I have to do a search on the key array to find the thing that I'm looking for, to decide whether there's a match that I want or whether I need to go left or right. So the most basic way to do this is just a linear search. So if I'm trying to find key 8, I just start at the beginning of my sorted key array, scan along until I find what I want, and I'm done. Right? Worst case scenario, I have to look at all k keys. Binary search, if it's sorted, then I just find the middle point, jump to that, figure out is that less than or greater than the key I'm looking for, or the one I am looking for, and that tells me whether I go left or right. In this case here, I'm looking for 8. I land on 7. I know 8 is greater than 7, so I can jump over here. Then I take the halfway point of that. I get 9. Then I go to this direction, and I get 8, and I find what I want. One thing, though, that is kind of cool you can do, if you know what the values actually look like for your keys, or actually what the keys look like, is that you can use an interpolation technique where you can approximate the location of the key by doing some simple math to figure out what your starting point should be for your linear search. So rather than in case of linear search, you start from the beginning and go all the way to the end. If I know that my keys are, in this case, integers, and I know something about their distribution, then I can do a really simple math and say, well, I know I have 7 keys in my array, and the max key is 10, and I'm looking for 8. So if I take 10 minus 8 and get 2, and then 7 keys minus 2 and get 5, I know I can just jump to the 5th position, and that's at least a starting point for what I'm looking for. So this obviously works because they're always increasing in monotonic order, right? If they're floats, this is harder to do. If they're strings, I don't think you can do this. But this is another technique you could do to make that search go faster. This one, I don't know how common it is. The binary search is, I think, what everyone does. But again, there's this trade-off now. In order to make binary search, I have to make sure my keys are in sorted order. If I'm doing the linear search, I don't have to do that. So therefore, as I update the nodes, I don't pay that penalty of maintaining the sort order. All right, so let's finish up real quickly. Talk about some optimizations we can do to make it go better. So these are the kind of things that, like, again, a real database system would actually do to make B+ trees go faster. So the first 2 things we're talking about are different ways to compress the data. So the first kind of compression scheme we can do is called prefix compression. And this is based on the observation that because we're keeping the keys in sorted order, it's very likely in a lot of data sets the keys that are stored in a single node are actually going to be very similar to each other, right? Because we end up sorting them, right? So in this case here, I have a node that has 3 keys: robbed, robbing, and robot. Well, all 3 of them share the same prefix, ROB. And so rather than me duplicating or storing that redundant ROB over and over again for every single key, what if I extract that out, just store the prefix once, ROB, and then for the keys, I just store the remaining parts that's actually different. So this is very, very common. These are called sometimes prefix compression, prefix trees. This is widely used in a lot of high-end or a lot of large database systems because there's so much duplicate data. So Facebook uses this for all their internal MySQL stuff, and it makes a big difference for them, and they save a lot of space. So this is just sort of one way to do this. There's other optimizations you can do, like if I'm doing a clustered index where I know all my tuples, the tuples are on disk or on pages in the same way that they're sorted in my index, then it's very likely that tuples in the same node, their record ID will have the same page ID because they're all going to land on the same page. So rather than storing that page ID over and over again for every single tuple in a node, I just store the page ID once and then store their offset or slot separately. Right? Yes?
I'm sorry. If you're doing something like this, then how does the system choose what prefix to use? Because, for example, here you have 2 things that start with ROBB. I know in this case it's like 3 things, so it's kind of obvious. But
yes.
How does it choose?
The question is, how do we actually decide what to do? Right? So you basically can say every single time I insert, I figure out what the common prefix is, and that's what I'll store. You could say anytime I do like a compaction or do like a reoptimization, then I decide what the best thing for for my keys right then and there. In practice, also think of it like in a lot of database systems, the newer keys might get inserted in always on the one side of the tree, like it's always increasing in value, and so therefore a large portion of the tree on the other side is going to be static. It's going to be mostly read only. So at that point, I can make it a hard decision. Like here's how I want to do compression and compaction. Different trade-offs. You can do it online or offline. Yes.
How do you deal with if someone inserts the word sad or something like that, right?
So the question is, what happens if someone inserts the word sad, right, and it ends up in this node? Then yeah, you have to account for that. You have to maintain it on the fly.
You have to remove the prefix or something.
Correct. Yeah. Or you could say, you can store some additional metadata to say this prefix is only used for the first 3 keys, not the other ones. Right? There's a bunch of different tricks you can do. So the opposite of prefix compression is suffix truncation. And the basic idea here is that we can recognize that we don't maybe need to store the entire key in our inner nodes to figure out whether we want to go left and right. So in this case here, we have ABCD up to K for one key, LMNO up to V for another key. But if I'm just trying to see whether I want to go left or right, I can probably get by just looking at the first, in this case here, first character. So instead of storing the entire key in the inner node, I'll just store a uniquely distinguishing prefix of it and then throw away the remaining suffix. So in this case here, I could have just stored L and A and L, and that would have been enough, but I'm showing ABC, LM, and N. Right? And again, down below, I still have to store the entire key because I need to go be able to have that and be able to say, is the key I'm looking for here? But in my inner guidepost, I don't need to have this have the full key. And of course, again, you have to maintain this. If somebody inserts something that would violate this, we have to reorder it or reorganize it. But in practice, if the data is not changing a lot, then this could be another big win. So as far as I know, prefix compression is more common than the suffix truncation. All right, the last 2 things I want to talk about is how to handle bulk inserts and pointer swizzling. So in all the examples I showed so far, we assume that we're incrementally building out our index. We're inserting keys one by one. But in a lot of cases, you have all the keys ahead of time. So it's a very common pattern that people do in databases that, say I want to bulk load a new data set. I collected data from some other source and I want to put it into my database. A lot of times what people do is they turn off all indexes, bulk load the data, insert it into the table, and then they go back and add the indexes. Right? So that way, as you're inserting the new data, you're not trying to maintain the index, which is expensive. So in this case here, if you have all the keys ahead of time, a really simple optimization to do to build the index is rather than building it top down like we've done so far, you actually build it from the bottom up. So let's say these are the keys I want to insert. The very first thing I do is just sort them. And we'll see in a few weeks, there's an efficient algorithm we can use that can sort data in such a way that maximizes the amount of sequential I/O we have to do. So we can sort it, and that's going to be way more efficient than actually building the index one by one. And then we just lay it out along leaf nodes, have everything filled out correctly, and then going from the bottom to the top, we just fill in the inner nodes and generate our pointers. So again, this is a pretty standard technique that any major data system will be able to support when you call create index on a large data set that already exists. And then once it's built, then I can maintain it or do any changes I want just like before. There's no real difference to it. The data system doesn't know whether you did the bulk insert versus the incremental build to build the index. Everything's still the same. In the back, yes.
So what if we want to merge a small lookup tree into a large lookup tree?
So this question is, what happens if you want to merge a small B plus tree into a large B plus tree? Let's take that offline, and we have a paper that does something like this. But I would say in general, building indexes with bulk inserts very fast is a very, very hard problem, and it's, at least in academia, it's underappreciated. This is very, very common. So having your data system do this as fast as possible is super important. So let's talk about that afterwards. All right, the last thing I want to talk about is called pointer swizzling. So again, I talked about how the way we figure out how to traverse the index is by having these pointers from one node to the next. In actuality, what we're storing is not raw memory pointers. We're storing page IDs. And whenever we want to do traversal, let's say we want to find key greater than 3, we start here and we say, oh, I want to go to this node down here. Well, how do we actually get there? Well, in the root node, I'm storing a page ID for this index, and now I got to go down to the buffer pool and say, hey, I have page 2. If it's in memory, if it's not in memory, go get it for me, and then give me back a pointer to it. So then I go get now my pointer to it, and now I can do my traversal. Same thing as I'm scanning along here. I want to get to my sibling. My sibling is page 3 because that's what's stored in my node. I got to go down to the buffer pool and say, give me the pointer for page 3. So as I'm traversing, I keep going back to the buffer pool manager and saying, do this conversion from page ID to pointer. And this is really expensive because I had to protect my hash table in my buffer pool with latches, and therefore, I'm going through a bunch of steps just to get this pointer. So with pointer swizzling, the idea is that if I know all my pages are pinned in memory, meaning I know it's not going to be invicted, well, instead of storing the page ID, I'll just replace it with the page pointer. Because I know if it's pinned, it's never going to move to a different memory address. So now when I do traversals, instead of doing that lookup to the buffer pool, I have exactly the page ID, or the page pointer that I want, and I can go get exactly the data that I want. And I don't have to go ask the buffer pool. Of course, now I got to make sure that if I evict this thing, and I write it out the disk, I don't store the page pointer, because when it comes back in, that's going to be completely different. So you don't blow away the page ID entirely. It's just you have a little extra metadata to say, here's the pointer you really want, not the page number. So you may say, all right, when would we be pinning these pages in memory? Well, maybe not for the leaf nodes, but at least for the upper levels, the root and maybe the second level, those things are going to be super hot because I'm always going to have to go through them to get down to the leaf nodes. So maybe it's not that big of a deal for me to pin those pages, and then they're going to be relatively small compared to the size of the entire tree. And then I can use this optimization because I know my pointers are always going to be valid. So this one is actually very common. Pointer swizzling is used in pretty much every major system. Okay? All right, so to finish up, the BB plus tree is awesome. Hopefully I've convinced you that it's a good idea to use this if you're building a database system. Next class we'll see some additional optimizations for this, and we'll maybe do some demos with Postgres and MySQL. But then we'll also talk about 2 other types of tree-based indexes we may want to use. Tries or radix trees, which are going to look like B trees but slightly different because they're not store entire keys. And then inverted indexes will allow us to do full key searches. Any questions? Today, we want to continue our discussion on talking about tree indexes. So I want to spend a little bit of time in the beginning doing some demos and discussing more about B plus trees to finish up the things that we left out last class. And then we'll talk about different ways, we'll talk about more ways you can use indexes beyond the straight key mapped into a data structure that we've been talking about so far. And then we'll talk about an alternative to B+ trees, tries or radix trees. And we'll go through what makes these unique, what makes them different, and how are they better or worse than B+ trees. And then we'll finish up really quickly with a sort of a brain dump of inverted indexes. I'm not going to teach you how they work. We have courses here at CMU that can do that. This is just so you know that these things actually exist. So when you go out in the real world and you realize that the thing you want to index can't be indexed in a B+ tree, you want to use one of these inverted indexes. All right, so the last class, we had a couple questions about how do we actually going to handle duplicate keys in our B+ tree index. So I showed you how we would handle duplicate keys inside of the node, right? We could duplicate the values in the node, and then or just have a mapping from a key to a value list inside the node. So now I want to talk about what I realized I missed out was discussing at a higher level, actually within the tree itself, how do we can actually maintain these duplicate indexes or duplicate keys. So there's two approaches to do this. So the first is that we're going to make every key unique automatically by appending the corresponding tuple's record ID to the key that we're inserting into the index. So instead of just storing the key, the copy of the attribute that's in the table, I'm also going to put at the end as a suffix the record ID for that tuple. So now that makes every single key automatically unique. So the reason why we can do this, and this still works, is because we're using a B+ tree. Remember I said it with B+ tree, we can do partial key lookups and still find the things that we want. So if I have an attribute or an index on attributes A and B, if I want to do a lookup on A, I can still do that without having B. So in our case, in the B+ tree, because we're not going to have the record ID, we can just do the regular lookup as we would with a key, but we just scan along the leaf nodes till we find all the matches for that given key. You can't do this in a hash table, right? For the hash table, you have to have the entire key. So in order to do this approach, you'd have to have when you do a lookup, the key you want, and then the record IDs, the record IDs they correspond to. But that seems stupid, because if you had the record IDs, why would you use an index to look up the record IDs? Yes?
So how will you generate this unique record ID, as in you are going to use some kind of hash function?
So his question is, what is this record ID? It's the page ID and offset we talked about in the very beginning, right? That's the unique identifier for every physical location of a tuple. Now, it may change, and therefore we have to deal with that. And Postgres is most famously the one where this won't work because they can move things around. But when we talk about multi-versioning, we'll see different examples of why this works for Postgres. This doesn't work for Postgres, but it works for other systems. But just assume it's a page ID and offset. Or in the case of SQL Server and Oracle, it was like file number, object number, page ID, and offset, like a more complex thing. The other approach is to somewhat violate the sanctity, if you will, of the design of the B+ tree and actually store the duplicate keys as overflow leaf nodes. So instead of expanding the leaf nodes horizontally to accommodate new entries, we're actually going to expand them vertically. And then within a given leaf node, we'll add these overflow pages, almost like the chain hash table we talked about before, and just add all the duplicate keys down there. So as we'll see in a second, I'll again provide overviews of what this looks like. This approach is going to be more complex because now we have to handle the case of where I'm scanning along my leaf nodes. I have to know how to follow those, follow down the overflow pages. If I'm scanning reverse direction, where do I start my scan when I jump back in the other direction? So most people implement this one. This has the advantage that, again, we don't have to make any major changes to our data structure, whether it's a unique versus non-unique index. Everything just still works the same. The downside is now we're actually storing this record ID as an additional key, element of our key, and that increases the size of our index. The amount of data it takes to actually store the index. With this case here, we're not storing any redundant information unnecessarily to make things unique, but now we have this management issue. So let's go through both of them. So this is our simple B+ tree that we talked about before. And so the first approach is, again, to append the record ID. So either I'm showing just like the key value. Let's assume there's an attribute A, and here's all the values for them. In actuality, what the database system is actually storing is a combination of the key and then that record ID. So now when I do a lookup and say I want to insert key 6, I would, at this point here, I can do a prefix search in my B plus tree because I don't have a record ID as I'm inserting this. Actually, I take it back. You do have a record ID, but I'm not going to find an exact match for that. So I would traverse down here and I would land to this page. The real thing I'm starting is the page ID and offset. But I land here, and now I know I want to go into this page. So because now I don't have overflow pages, I have to go exactly in sorted order. So assume whatever this original 6 is, its record ID is less than the one I'm inserting. So it needs to go between the 6 and 7. So I just do the normal split process that we talked about before. I slide everybody over, 7 and 8 move here, and now I can update pointers and how 6 goes in here. Right? It just works exactly the same way we talked about before. If I want to do a lookup on 6, again, I just do the prefix search. I just look at the first element of the key, just the 6, and I can find down here now, I scan along my leaf nodes until I find what I want. The other approach is the overflow pages. So now, again, I want to start 6 again. I know I want to go into this guy. I don't want to split across, right? I don't want to do what I did before and have 7, 8 move over. I want to go in this page here, but I can't because it's full. So I just add now an overflow page where I insert my new 6, and now I have my pointer down to it. Now remember I said before that in most textbook definitions of a B plus tree, you assume that the keys are always going to be sorted within the node. In this case here, we could do that. We could sort them, but it's not actually wrong to leave it unsorted. We just need to know when we're looking for the element that we're looking for. We can't use binary search to jump around. We have to do the linear search to find that we want. So now let's say I want to insert 7. Same thing, 7 goes down there. I insert 6, same thing, 6 goes here. It's unordered, and that's OK. So now here's what needs to happen. So physically, this is stored across multiple pages. Logically, from the index's perspective, this just looks like one giant leaf node that has a bunch of in it. So now if I'm scanning across, I do the same thing. I follow this pointer, I land here, and now if I'm scanning across, instead of jumping over to this node, I know I need to follow my overflow page and keep looking there. And eventually, if I find what I'm looking for, I'm done. If not, I need to go to the next page. Then I just follow that pointer over there. So now I may be thinking, well, why not just have this guy? Shouldn't this guy really be pointing to that one, right? Because that would actually be correct. But now the problem is every single time I add a new overflow page, not only do I need to update my pointers internally for these nodes over here, I now need to go update this one as well. But if I just leave that pointer alone and let it point to the beginning of my page, the topmost leaf node in this vertical tower, then I would just land there and say, oh, well, I'm going reverse search. I really need to jump to the end of my overflow page and work backwards. There's a bunch of extra logic we have to do to accommodate this. Yes?
I have a trivial doubt. So whenever...
Sorry, say it again. What was your first word? Sorry?
Sorry?
You haven't reviewed what? Sorry?
No, I have a trivial doubt, a question.
Oh, wait, a doubt. OK, yeah.
So it's that whenever we get something like fetch 6, so what the system actually asks us to fetch all the pages corresponding to the key. So key 6. So we need to fetch all these 3 pages back.
So his question is, if the data system is using the index, and we're trying to find the tuples that have the value 6 for this particular key.
Right.
So what is the index returning?
Yeah.
Well, it would return the record IDs. So you would say, you basically have an iterator. I traverse down, get to my leaf node, and now I'm calling next on this iterator, and I'm looking at every single element until I find the ones that I want. And I know the iterator knows to stop, which says, I'm looking for everything where key equals 6. So as soon as I see maybe a 9 over here, I need to stop. But this is what I'm saying. If this is unsorted, then I know I need to scan to the end of all my overflow pages because the last 6 might be here.
Yeah.
If I want to keep them sorted, then now I insert this 6 here. Now I got to go update this guy and this guy. Whereas before, if I just append it only, I'm updating one page. So this is a really good example of why trying to understand these data structures in the context of a full system is important. If you take an algorithms class will teach you, yes, this is the way to start a B plus tree. But now, because we're inside of a database system, we know we have these things called record IDs, and we can exploit them to facilitate different aspects or different operations that would not be otherwise easy to do. Yes?
Presumably for the overflow, we continue to another overflow.
Correct. So his statement is, if this thing overflows, we just keep continuing. Yes?
Then, presumably there's a certain point when you want to actually rebalance.
Correct. And then he says, to a certain point, you actually want to rebalance. So Yes, so that could be a criteria that says, all right, well, if I go beyond this number of overflow pages, then do a split. But if these are all 6s, right, in a single page, then you can't quite easily do that without appending the record ID. All right, cool. So let's do a demo because we didn't get to do this last time. So we're going to do Postgres, and I just want to show the difference between a B+ tree and a hash index. All right, let me turn this off. All right, cool. Let me log in over here. So I'm going to have a table. Is this live? Yeah, OK. So this is Postgres. I'm going to have a table of email addresses. So it's going to be a simple table with an ID, with an auto increment key, and then a bunch of email addresses. So this is a file that you can find on the internet. This is a list of 27 million email addresses from. If you don't know what that is, it was think of like Tinder before Tinder. It was an adult hookup site in Canada that got hacked, and then eventually people released the email addresses. So this is real. It shouldn't take that long to load, but I should have done this beforehand, but that's OK. So what we're going to do is we're going to create 2 indexes. We're going to create a hash index. So in Postgres, you can actually say when I want to create an index, I want it to be a hash index. And then you can then say, I want to create an index, and I want it to be a B+ tree index. Of course, yeah. Well, this is that in a good demo, right? OK. So maybe we'll come back to this. Let's go to MySQL. Sorry about that. OK. So same thing. This is MySQL. So I can do select count star from emails. All right, Postgres finished. Actually, let's go back to Postgres because it's done. All right, it took a minute. So I told you I inserted 27 email addresses. So first I'm going to do is I'm going to create a hash index. So by default in SQL, in most systems, if you just create an index, you're going to get a B+ tree, or some tree data structure. In Postgres, I can say using hash. So I'm forcing it to use a hash index. And so now we can see things like, of course, now I got to load this. I should have warmed it. Sorry. This shouldn't take too long. But we can see how if we try to do certain queries, we won't be able to find the things that we want. Let me load all this in. Sorry. PG warm. So this is that same function I used last time, just to warm the cache. And then now when I call create index, in theory, this should be faster because everything's just loaded in. But we're going to run queries, and we're going to see how the query planner is not going to be able to pick the index for some queries, but it'd be able to pick indexes for other queries, right? Because a hash index, again, you have to have the entire key, or the entire elements of the key. You can't do partial lookups, and you can't do range scans. Sorry. Well, this sucks. All right, while this is going on too, I'll then create the B+ tree index in the background. I had everything working, and then I dropped the table right before class started, and I forgot to rebuild it. All right, we're back. OK, so it took 50 seconds. All right, so now I can do, say, queries like select star. Let's find a user first. Select star from, let's find the minimum email address from emails. Yeah, there we go. Whatever that is, someone correctly used a fake email address. So if I want to do select star from emails, where email equals this thing, again, if I add that explain keyword, Postgres will tell me what it's going to do. So Postgres is going to tell me that, hey, I have this thing called a hash index, and I can do a lookup because I know I can do exactly the thing I'm looking for will equal that text. Right? We'll ignore what a bitmap scan or heap scan is. That'll come later on. But we know this is going to be fast because it's going to go find exactly the one that we're looking for, right? But now, say if I want to do something like where email like, and then this thing, and put a wildcard at the end, can you use this hash index? No, right? Because you have to have the entire key. I'm not going to run it because it'll probably take the whole time, but they can tell you when you're asking explain, it tells you it's going to default to the sequential scan. Remember, the sequential scan is always the default operation or access method for the database system. If it can't find what it wants using index, it always defaults to a sequential scan. So while this is going on, let's build the tree index. But we can see some other things too, right? So let's say we want to count all the email addresses that are greater than this. Right? Can it do that? No, again, right? Because we have to have the partial key. We can't do anything that's not in the quality predicate. It always has to be an exact match. Right? It can do some things though, right? So let's say we find let's say somebody else also did this one too. Whether that exists. I didn't find that. But actually, that was pretty fast for a sequential scan. No, wait, sorry, that's an index scan. So let's find another one. Let's find another one. Let's find somebody who starts with an A. So like A star, and then we'll limit 1. And this basically says just find me the first one that matches that. Right. So there's somebody's email address. That looks, but that's okay. But we can do other things like this, or email equals like that. And it was able actually to do 2 index scans. So Nose has an OR clause, and you can see I'll do one probe in the index, try to find what I want, do another probe in the index and try to find what I want, and then it combines them together. And that's what the bitmap OR means. Basically what's happening here is the bitmap index means that it's trying to find all matches, and then instead of storing the record ID, it maintains a giant bitmap, and then just stores it sets that bit at that offset to say that record matched, and then it combines them together, and then it produces the output. So that's why it sort of has to do this, and then another lookup over here. All right, so now our B+ tree is done. So now we come back to our original query here. Yes?
In last class, didn't you explain that it will do only one search and it will organize the search in a way that both of them are being done together?
Your statement is, didn't I say last class that it would do the search once and then organize it?
It will go through the B tree down one.
This is a hash index. This is the B plus tree. Sorry, this is a hash table. This is not a B+ tree. Okay? Like going back to, well, now I just added the B+ tree. But yeah, right there. So this is explain. Explain is telling you what the query plan is going to be. So it tells you I'm going to do an index scan using IDX emails hash. That's the name of the hash table index I created. Okay. So now I have my B+ tree index. So if I do something like this, just do this lookup we had before, this fake email. It tells me it wants you to hash using the hash index. But as soon as I add this, I add the range predicate down here. Is it going to use the hash table? No. It's going to use and actually use sequential scan. All right, this is another good example. So this guy is the smallest key that we have in our index. So it knows that if I want to use the index, then all I'm really doing is jumping to the far left point and just scanning along the leaf nodes. And so therefore, the traversal of the index was a waste of time. Therefore, it's better for me to just do a sequential scan. But let's say if I change that to Z, a bunch of Z's, and now it says that, all right, well, I know that if I use my index, I'm going to throw away a lot of data. So now I can use that tree to jump down to the right side of the tree, get a starting point, and then scan along the leaf nodes. Right? So there's this internal cost model thing that's going on in Postgres that we'll talk about later that allows it to decide when's the right time to do these things. So is this clear? So for quality predicates, the hash index is going to be pretty good. But for these range predicates, if it's at the right location, again, we know something about the distribution of values, then it will choose to do an index leaf scan. So now if I go back here, again, this guy was doing the index scan, doing exact point query lookup. If I drop that index, drop index emails hash, comes back right away. And now I do that predicate. Now it's smart enough to know, oh, I no longer have that hash index, but I do have this tree index, so I can use that for this quality predicate. So is this clear? All right, the other thing we talked about last class briefly was table clustering. So table clustering is where we're going to use the index to enforce the sort ordering of the table themselves, the tuples themselves. So remember, Postgres is unsorted, or sorry, the relational model is unsorted. So as we insert things into Postgres, it's just putting them in essentially the order that it was told to put them in, like, as we do the inserts. And we saw examples where I can update things, delete things, and I can reshuffle them depending on how what free slots are available in a page. So if I go, say, do a select query here, select star from emails, and I just say, give me the first one. All right, we get some random Gmail account. But now if I say, if I call this clustering command, this will take about a minute. But what this is doing, this command is forcing Postgres to essentially resort the entire table based on the sort ordering defined by this index. But this is a one-time operation. So as I modify the table and maybe things get out of order, it's not going to match what it was when I first set it up here. Some systems, like in MySQL and SQL Server and Oracle, you can say I want an index clustered table or an index table clustering on the index, and therefore it ensures that no matter how you insert values into your table and what order you insert them, the underlying physical storage will be sorted. So in some cases, this allows us to do binary search directly on the table themselves, which is still log n, but without having to go through the index itself. So this is going to take a long time, so we'll just let this go. But I quickly want to jump back over to MySQL. So again, same email address, load it into MySQL. I can do the same kind of queries, select star from emails, wherever that fake one was. Email equals that. So the MySQL explain is not as good. But basically, it's not a tree structure. But you read it here. It says, here's the index I could possibly use. So it knows I have a hash index, and I can use that. And then if I do change that to be greater than this, still uses it. No, but it says here it's kind of hard to see. It's small. It's rolled over here, but see there's this column here called rows. This is MySQL telling you how many rows I think I'm gonna have to read. So that's 27 million wrapped around here. So it could use this hash index, but it's gonna fall back and do a simple sequential scan. Whereas the one up above, it could do an index probe to find exactly what it wanted. All right, so Postgres is now done. We're coming back here. So now if I do limit 1, right, I get that first guy that I had before. Right, so this is saying, again, give me the very first tuple you find for this, and this is the min one that we found before, because this guaranteed that this was inserted order. So if I do this now, if I say I delete that email address, delete emails where email equals this thing, I go ask for the first one, and now I get a different fake email address, but now let me insert another one back in, insert into emails, values, default, because it's an auto-incrementing key, insert my guy back in. Right, it's still not in sorted order, because it only did that operation once. Any questions?
So you have to run cluster again and again to make it sorted.
His question is, to enforce sort order, I'd have to run cluster over and over again. For Postgres, yes. For other systems, you do not have to do that. You can say, I want it to be automatically clustered by the index.
And does the column needs to be indexed before we cluster?
This question is, does the column need to be indexed before we cluster? No. So in MySQL, it's sorted by the primary key. So in MySQL, the leaf nodes are actually the tuples themselves. Yeah. So as I'm moving things around, splitting and merging, the leaf nodes will always be in that sort of order. So if I want to do a sequential scan on the table, I'm basically always following the leaf nodes. And so in other systems like Oracle and SQL Server DB2, you can say, create this table and sort it by these columns. And it'll do it for you. Oh, sorry. Yes?
For duplicate keys, you said that we'll add the page ID and record ID at the suffix, right?
Yes.
So instead of that, why don't you use the timestamp when the record was inserted?
This question is, I said that we could use the physical ID, sorry, the physical location, the page ID, and the slot number as the record ID to determine, to make the tuples unique. Instead, why not use the timestamp of when the tuple was inserted?
Because the physical location can change, right?
Because if it, yeah, so in Postgres this is an issue. For MySQL this won't be an issue. What's the problem with timestamp?
The distributed setting, like time is.
He said in distributed setting the times aren't guaranteed to be synchronized. Yes, even more simple. That is an issue. Leap second, leap years, right? So now, again, they repeat the second. Now what happens? I insert something, now they have the same timestamp. Or clocks can drift. Like clocks are horribly inaccurate. So, you know, I run NTP every so often, and now it slowly drifts the clock, but occasionally it has to do big steps. You might repeat a second. Yes?
I suppose if you, like, what's the difference just being using like a millisecond, like epoch or something like that? It's like the timestamp.
His question is, what's the difference between doing the record date versus milliseconds versus the unique?
Like, so like if you do like milliseconds epoch or something like that, like then isn't that going to be unique and take care of the leap second because it just takes into account the milliseconds that leap second or leap
Yeah, so he's right. Milliseconds, since the unique clock would take care of a leap year, it won't help drift, right? If the clock has to get stepped back, you repeat seconds. Nobody uses timestamps in that way. You can use logical timestamps, which we'll talk about later on. You almost never want to use hard physical clocks. You use them in conjunction with other things. Yes?
When do you want to use the cluster if you already have an index?
The question is, when would you want to use a clustering index if you already have an index? So again, like in the case of MySQL, I should show an example. In MySQL, it's always a clustering index. When I call create table, it's always clustered on that. There are some cases where, for certain queries, you can be smart about like, all right, well, if I'm clustering on the logical timestamp when it was inserted, like the application told me the timestamp, then now maybe I can say, well, take the last day's worth of data and put it on the fast disk, and the older stuff puts on slower disks. There's ways to do like disk partitioning that way. And the data system can enforce that all for me underneath the covers.
I was wondering, like in MySQL, you said that all the things are sorted by the primary key. And
Yes.
say suppose we have the email and we do index on email.
Yes.
And we do the cluster on email.
Yes.
And we try to find something through ID. So wouldn't that be an issue because now everything is sorted based on emails?
So your statement is if I'm clustered on email, I have an index on email,
Yeah.
and that's my primary key, and then primary key is ID. So if you have a primary key, we'll see this in a second. You always have an index on that ID or on the attributes.
You cluster the location string, right?
Yeah. So then you have to update the other index. Yes. Depends how you store your indexes. We'll get to that later. Like, we'll get that when we talk about diversion. So the pointer could be the primary key, or it could be the record location, the record ID. You can do different things. Postgres does record ID, so you have to update all the time. MySQL does primary key. All right, so we actually can poke around in Postgres real quickly and see what roughly what the tree looks like. Right, so this is just an extension of Postgres that allows you to get information about what's in the tree. Right, so I can say I have this index called on the B plus tree, and I can say give me information about it. It tells you how many levels it has, tells you how many elements that it's storing, and the root block size. So then we can go even further, and we can actually inspect the contents of the tree with this command here. And the actual details doesn't matter, but there's a bunch of hex stuff. Right, so this is the root node. So we can go a bit deeper now and show you, for a single node, here's some information about it. But then that's all hex, but we can decode it. And then here's just proving that it's actually storing these emails. So this is saying that here's a record at offset 3 in my root node, or in this particular node in the tree. Here's the page number and offset where it's located. Here's the hex form of what's being stored, and then there's the actual email address. Right. So again, the data system is going to store entire copies of these keys on the inside. All right, we're going to stop now and keep going because we have a bunch of other stuff we want to get through. But that's just again to show you that you can. by default, you're always going to get a B plus tree, but you can force some systems to tell you, I want a hash index, and there's different trade-offs for doing this. All right, so now related to the point he said about the primary key, versus the cluster index. So if you create a primary key, the database system will automatically create an index for you. And actually, for any time you declare an integrity constraint, it will automatically create an index for you. And you think about it, it has to, because otherwise, the only way to enforce that is to do a sequential scan. So in my auto increment key, if I had to enforce the primary key uniqueness of it, every single time I inserted that unique tuple, if I didn't have an index, I had to scan every single tuple all over just to make sure there's nobody has the same key. So again, every database system will do this automatically for primary key and unique constraints. So basically, again, when I create the table, if I have primary key and unique, it's the same thing as running these commands. I'll create the table, then it goes ahead and creates these indexes. For foreign keys, it doesn't actually do this. So if I create a new table here called bar and has a foreign key reference to this value here, every database system that I ever try this on will always throw an error because it's saying it doesn't have a way to enforce this referential integrity constraint without an index. Right? You think it could automatically create one, but it doesn't do that because it doesn't know, because this has to be unique, right? So it won't actually do this. Instead, you just replace that with add the unique clause here, and that builds an index automatically for you that it can then use to enforce this, right? Because basically the way foreign keys work is that every single time I insert a new tuple into bar, I have to have this ID thing. So then to make sure that it matches to a tuple in this table, I then do a lookup in that index and see whether there is a parent referential match. So now I want to talk about different ways to actually use indexes beyond the copy the whole key that we talked about here today. So the first thing that we can do is what's called a partial index. So when you normally call create index on a table, it does a sequential scan across the entire table and looks at every single tuple. But in many cases, for a lot of applications, maybe you don't need to have an index on the entire table. And instead, you always want to maybe on some subset of the data. So this is what a partial index is. You basically modify the create index command, and you add this where clause at the end that tells you what tuple should match in order to be put into this index. So now, if I want to do a lookup like this, select B from foo, where A equals 1, 2, 3, and C equals Wu-Tang. So I've built the index on A and B. My where clause has references A, so I can still use this index, but I can also look at this thing and say, oh, where C equals Wu-Tang, then I know this is exactly the index I want to use. So then this allows me to do a more, the index is leaner because I'm not storing all the information for all possible tuples. I'm only storing exactly whatever it matches in my where clause. So if somehow the query doesn't have the C equals Wu-Tang, I can't use that index. So this is very common when people do things like they want to have different indexes for different date ranges. Like, per month I'll have an index so I can do lookup quickly on all the orders I want for that, for that month. And again, I'm trying to not have to pollute my buffer pool cache with a bunch of data that I don't need. By having a partial index, now the height's going to be lower, and I can quickly find the data that I'm looking for. So in this particular example here, for this query, we were doing a lookup on A using C, and we want to return B. It turns out, actually, for this particular query, all the data we need is in the index itself. So remember I said, normally the index would for a given key, would produce a record ID that you could then follow that in the table heap and get the tuple that you were looking for. But for this particular query here, we don't actually even need to even look at the tuple. Because we need A to do the lookup, that's in there. We need B, that's in there. And C is already handled by the partial index where clause. So to answer this query, we only need to actually look at the index. We never actually need to look at the underlying tuple in the table. So this is what is called a covering index. A covering index means that all the fields that are necessary to answer the required result for the query are produced, can be found in the index itself. Right, so you don't declare an index as a covering index. This is something the database system figures out for you automatically. It knows what your query is, it knows what your index, it says everything I need is in here. So again, just using this simple example, I can get the B field from that. The A and B field can be found exactly from the index, and I never need to look at the actual tuple. And I can do this for a bunch of different queries. I can do this for aggregations. I can do this for joins. And the advantage here, it's one less page ID lookup in the page table and maybe one less disk I/O to not have to go look at the underlying tuple for this. So a bunch of different database systems support this. All the commercial guys do. Mongo does. I don't think MySQL and Postgres do. I may be wrong about that. But this is a big win, right? If you can do this, this is a huge deal. Actually, I don't think Postgres can do this for reasons we'll talk about later. So for this simple example, this is great, right? I need A and B. A and B can be found in the index. But what if I have now another attribute that I want to be able to do a lookup on or get for my query, but I don't actually want to build the index on that attribute. Right, so my table has column A, B, and C. Maybe I don't want to index on C. But it'd still be nice to have a covering index, not have to go look at the tuple. So this is what the include columns allows you to do. Basically, an include column allows you to say, for all the keys that I'm storing in my leaf pages, my leaf nodes, also include these additional attributes. So in this case, I'm building index on A and B. All the inner nodes only have keys A and B. And when I do lookups, I only examine A and B. But when I land into the leaf nodes, I can also get the C attribute value for every single entry in there, right? So now, again, if I go back to my other query here, select B from foo, where A equals 1, 2, 3, and C equals Wu-Tang, I do my lookup on A, follow that down. Then as I'm scanning along the leaf nodes, I can look at the values at C that's packed in the leaf nodes and also evaluate my predicate and produce my output. So this one's more rare than the covering index support. So a lot of systems support the partial indexes. Slightly fewer systems support the covering indexes. This one is even more rare. I think this is Postgres 11 Postgres 11 is going to add this or has it now. SQL Server has it, but MySQL doesn't support this, and Oracle does not support this. So again, the key thing about this is that although we can do a lookup in C in our where clause, it's not in the inner node. So we're not greatly increasing the size of the overall index. The last kind of index I want to talk about are functional expression indexes. So again, everything we've shown so far, anytime we declare an index, we're always creating an exact copy of the key that's in the tuple and putting that in our index. But there may be some queries out there where we don't actually want to do a lookup on the exact value of a key. We want to do a lookup on some value that we derive from the key. So let's say I have a simple example here. I have this users table, and I want to do a lookup and find all the users that logged in on a Tuesday. So this extract function takes the timestamp, and you pass in what element of the date or timestamp you want. So DOW means day of week. And so this is saying extract the day of week from the login timestamp field and find the ones where it equals 2. Tuesday's 2, Sunday 0, Monday 1, Tuesday 2. So if I create an index like this, as we've shown so far, right, this won't work. Why? Yes?
So you have to know which dates which dates in whatever format you're storing will actually have.
Correct. So this one he says, you have to know how to extract out or pull out exactly what ranges will correspond to Tuesday. And so you can kind of be smart and say, oh, well, my query looks like this. I could say, well, here's the ranges of timestamps where Tuesday can be found. But as far as I know, no system actually does this. So instead, what you can just do is not use this and create a functional index or expression index where the attributes you're indexing on can be any arbitrary expression. Anything you can have in a where clause, you can build a index on. All right? So now when I want to do a lookup and for this predicate, I know how to exactly satisfy it by looking at every feed, just scanning along here, finding all the twos that match what we want. What's another way we could speed this query up too, that we've already shown before? The partial index way, right? So instead of creating an index for exactly in this way for the extracted day a week, I can instead just use that as my where clause to say put only the elements where the extract value produces 2. All right, so let's do a demo of this in Postgres. So Postgres has the partial indexes. It has the doesn't have covering indexes, and then the version I have here is 10, so it doesn't have the include clauses. But we can play around partial indexes versus the functional indexes. All right, so for this, we're going to create a table. Make sure we turn off parallel workers. And timing is on. All right, so we're going to create a table that has, again, ID field and a login timestamp. And then this is going to be a simple, this insert query is just going to insert a bunch of records, a bunch of unique timestamps since 2015 to now at 1-minute intervals, right? And this is going to generate, looks like 2 billion records. So in sake of time, we'll go make this go fast. So we'll PG warm everything. Now everything's in our buffer pool. So say this is the query we want to run. We want to get the average ID of users where the day a week is they logged in on a Tuesday, right? So in this case here, when we run explain, it has to do a sequential scan, right? Because there's no index. So the first index we can build is the expression index. And this shouldn't take long. So now when we run explain, we can see that it's able to pick out and use that expression index we just built, right? And again, the way it did that, it said, oh, I know you're trying to do a lookup on this particular extract function where the output is 2. So now I just need to do a lookup and say, find me all the values where it equals 2. So then we can add the partial index. Again, this is now creating a smaller index that only contains the enter, or did I? It only contains the records where that extract function equals 2. So now I go back to my function here, and I see now it actually wants to pick that index because that's going to be smaller, less. The tree has a lower height, and I can just find exactly what I want immediately. So again, the database system can figure out on its own which is the best access method to use for all these different choices. All right, so any questions about this? Yes?
If my expressional index is something like difference of the day from the current date, and now the date changes, then won't it lead to problems?
Okay, so he said, so let's try it out, right? So drop index. So his statement is, what happens if my expression is it's based on some difference, or using the current timestamp? Isn't that going to change every single time I run it? So I think what Postgres is going to do. So let's do the let's do the expression index. Where is that? Yeah. So he's saying do this. Take login. And again, I can put anything I want in here, as long as it's a valid expression. So I can say, take my login and subtract out now, the current timestamp. Doesn't let you do that. I forget how to do this in... Yeah, I forget how to do subtraction in Postgres. Can you do that? That works. Okay. Oh, because you have to do this. Okay. Nope. Nope. Let's do something more simple. Let's take login, subtract 100 from it.
But it won't change, right?
Didn't like that either. Yeah, all right, so basically what happens when we call create index, it'll run the now function once, and whatever that timestamp is now, that's now. Later on, it doesn't change. It's not dynamic. It's as it builds the index. So now if I insert something again, in theory, it should now use the current now. If it's smart, it could say, well, what was the now at the time when I built the index? I don't know whether it does that or not. But again, so you can't do certain stupid things like you can't do like 1, build an index on 1, but I should be able to do ID plus 1. No. Wait, what am I missing here? I think it's this. There we go, that's what it was. Right. It's double parentheses. So yeah, so now I can't, it won't let me do this. Without, no, I already, user login expr. Let's try his other example. Functions in the index expression must be marked immutable. So there you go. Yeah. But I should be able to do this, right? Like, nope, no times out. All right. Anyway, you get my point. Yeah. There's this thing called, we'll talk about snapshots later on, but like, there's like the now at the time the query runs, and it has to be guaranteed that's consistent at for the snapshot of the index itself. Yes?
Some concept confusing. I mean, when we create index, which kind of index will we create? Like a pathway or a...
So this question is, when we create an index, what kind of index is it going to create? So by default, it's going to create a B plus tree. If I add that using clause from before, so but this is a Postgres idiom. This is not in the SQL standard. So if I add this using hash, this tells Postgres, make me a hash index. By default, everyone's usually going to get a B plus tree.
And when we add index, I mean, we can boost performance, but the reason is we don't need to search the tuple in the leaves, all right?
Your question is, when you add an index, you can make
the performance better, right?
Yes.
But the reason is, I want to ask the reason. The reason is we search faster, or the reason is we don't need to look at the leaf nodes anymore because we have all the information in the index.
Sorry. So when you say you don't need to look at the leaf nodes of what? The index?
The information, like we select something.
So I think your question is, if I have an index, and if I do a lookup, for some queries, I don't have to look at the actual tuples. I can just look at the indexes. Yeah. You were calling, like, the tuples are, in the table heap. They're not leaf nodes. The leaf nodes are in the index, right? So I always have to look at the index because in a B plus tree, I always have to go to the bottom. Okay. So for some queries, if you can do a covering index lookup, I never have to look at the table, the tuple. I can get all the information I need to compute the answer from the index itself. Not all database systems support that, though. So for what we've talked about so far, other than covering indexes, the idea is that we can quickly find the tuples that have the keys that we want to look up on without having to do a sequential scan. So sequential scan is n. If it's a hash index, I can do O1. If it's a B plus tree, it's log n. Right. So the idea is cutting down as much data as you can to not do wasted work.
Yeah. So if we create a table and there's some data but with no index, then we have to do the sequential.
Correct. The statement is if we create a table and there's no index, we always have to do a sequential scan. Yes, we saw that at the very beginning. Yeah. Yes.
And if you create an index, does it create the entire data structure in the memory?
The question is, if I create an index, where does it live? Well, again, if it's backed by disk, it goes, it gets written out. If it's backed by the buffer pool, it goes out to disk. And I want to do that because my index might be larger than the amount of memory that's available to me. So again, I could have an ephemeral data structure that's in memory, and I have to blow that away. MySQL does that for their hash table because it has to be in memory. But the B plus tree is backed by disk, so as it gets too large, I page things out.
Okay, so we'll have some we have our table separate and index separate. So that is
what do you mean by separate?
Separate in memory, separate memory.
It could be the same buffer pool. It could be different buffer pool instances. It depends on the implementation. Again, the buffer pool manager doesn't know what's inside the pages. It just says, you want page 1, 2, 3? Here it is. and then whoever is accessing it is responsible to know how to interpret those bytes. The buffer pool manager doesn't know, doesn't care. In the high-end systems, you can say, here's the buffer pool manager for indexes, and it has certain replacement policies, and here's one for tables, and they have another replacement policy. But for Postgres and MySQL, it's all the same. Okay. So let's now jump back and finish up with tries. Okay. So in all the examples I showed for the B plus tree so far, the inner nodes and the leaf nodes always had an exact copy of the keys. Yes, you can do prefix compression or suffix truncation, as we talked about last time, but in general, we have the entire copy of the key replicated multiple times throughout the tree structure. And so the other issue is going to be also in a B plus tree is that in order for me to determine whether a key exists in my table, I always have to get to the leaf node. I always have to traverse all the way to the bottom, right? Because again, the inner nodes may have copies of keys that no longer exist. Because when I delete them from the leaf node, depending on how I split and merge, I may have left my guideposts up above. So in order to determine whether I know exactly this key exists, I always have to go to the leaf node. So this, again, it's log n instead of on, which I have to do a sequential scan, but it's still not great. And I may have, depending on how much memory I have and how I'm using my buffer pool manager, I may have a page miss where I have to do a lookup on disk for every single node as I traverse down. So for some applications, it might be nice if we can actually figure out at the top of the tree whether our key exists without having to go all the way to the bottom. So this is what a try does for us. So quick show of hands, who here has heard of a try before? Okay, perfect. Who here has heard of a radix tree? Fewer, excellent. Okay, so radix tree is just a specialization of a try. And nobody uses tries, everyone uses radix trees in databases. So we'll go through this. So a try is a tree data structure where instead of storing the entire copies of keys in our nodes in the tree, we're instead going to store digits of the key. And by digits, I don't necessarily mean Arabic numerals. I mean some subset, atomic subset of our key, like a byte, a single bit. And so what happens is that we're basically going to decompose all our keys and store them down, the digits down, at different levels, one by one. And then now, because we could have duplicated keys or duplicated digits, we only need to store that once at each level. So a really simple example here would be a try like this, where I have 3 keys, hello, hat, and have. So in the first level in the root node, all 3 keys begin with the letter H, so I store H once. And there's a path down to the second level, where now I distinguish between hello and hat and have. Hello has an E, hat and have an A for the second digit. So I have separate entries for that, and then now I have separate paths down to handle for each unique path in the key. So now if I want to do a lookup, say I want to look up a hello, I just decompose the key into its digits, and I look at the H, I have a match here, I find the E, and then I traverse down the LLO. And the bottom is just like in our B plus tree, this could be a record ID that points to the actual tuple that we're looking for. So tries are old. Tries are older than B plus trees. Remember, B plus trees were invented in like 1973 at IBM. Tries are actually invented in like 1959 by this French dude. And he didn't have a name for it. And then there was this another CS researcher, this famous guy, Edward Fenkin. And then a year or two later, he proposed the name try, which is short for retrieval tree. And he was using that to distinguish from a regular tree data structure. So this is why they're called tries. And apparently this Edward Fenkin guy is actually CMU faculty. If you go look at the CS website, the directory, he's listed there. He's like super old. I've never seen him at any faculty meeting. I don't know who he is. I don't know if he's actually still here, but that's the guy that invented the term try. He's actually here at CMU, supposedly. So sometimes you also see these things listed as digital search trees or prefix trees. As far as I know, these are all the same thing. So tries are really interesting, right, in the context of databases, right? Especially now that we understand B plus trees. So the first thing that's super interesting about them is that their shape only depends on the key distribution of the key spaces and their length. So what I mean by that is that it's a deterministic data structure. So no matter what order we insert the keys, we're always going to end up with the same shape of the physical data structure. Right? That's not the same thing as in a B plus tree, because in a B plus tree, if I insert a keys one way, and then I shuffle them around, and I insert them to another tree, depending on how I do with splits and merges, I may end up with different layouts of the nodes. The keys might be in one node versus another node. In a trie, it's always the same thing, right? The other thing about them is that they don't actually require any rebalancing like we had in the B plus tree. So we'll see, there is some rebalancing we could do at the vertical level, but horizontally, we're never actually going to potentially rebalance. So, and unlike in a B plus tree, where all the operations were log n, in a trie, the operation complexity is k, where k is the length of the key. Right, this is totally different than a B plus tree. So going back here, so if I want to look up hello, by the time I get here, I know that there's no, I keep going down the bottom, but so the number of steps I have to do is dependent on the key that I'm looking up. But say I'm going to look up Andy, A-N-D-Y, the first letter is A, I look up in the root node, I see it only has an H, I immediately stop and I know the thing I'm looking for can't be anywhere else in the tree, and I don't have to always traverse to the bottom. Yes?
For the E, don't you have to iterate across that entire block?
Your question is, for the E here, do I have to iterate across the entire block?
You have like a bazillion, like it's not letters, but it's like some not like really large thing. Like you have a bazillion, like a really wide block there. You have to figure out which one you want to go down.
So the statement is, if this thing is super wide, does that mean I have to sequentially scan across the entire thing? You pre-sort them. Okay. Right? You do binary search to find the thing you're looking for. Well, when we see actually how we actually do this in for bytes, you can just jump exactly to the position you want. It's either there or not there. Yeah, this is not really a physical diagram of how it's actually stored. This is just a high-level overview. Okay, so again, this is super interesting because the fact that the complexity is based on the key that we're trying to look up on the length. It's also interesting because now we're not storing the exact copy of the key, directly in any single node. It's implicitly stored by the path. So if we want to reconstruct hello, we would traverse down, keep track of our path on the stack, and that's how we can put the key back together. Whereas now this makes sequential scans more difficult because although I can be in sorted order, I got to backtrack and go back up and go back down, unlike in the B plus tree where I can just scan along the leaf nodes. So tries are going to be faster for point queries than a B plus tree, but they're going to be slower than for scans. All right, so now we get a bit more formal. Talk about the definition of a trie. So we would use the term span the same way in a B plus tree of a node, just to say the span is the number of sort of outgoing branches. This is essentially the number of digits we're going to represent at each node in each level. So if a digit is going to exist in the corpus, then at the level at each digit, we'd have to have a pointer down to another branch. If it doesn't exist in our corpus at a level, then we just store null, like a null bit or something. So now this span is going to to determine the fan out, just like again in a B plus tree, and that's going to then correspond to the physical height of the trie. So the parlance, you would say, I have an n-way trie. You would say you have a fan out of order n. Again, it's the number of paths coming out. And that's going to determine the size of the digit you're storing at each level. So the most simple trie you can store is a 1-bit trie. Right? So at each level, I'm going to discriminate a digit of a single bit. So let's say I want to store these 3 keys, 10, 25, and 31. So it's a 1-bit trie. So I mean, at each level, we're going to look at 1 bit. So I'm showing them in, here's the binary form of these 2 numbers, or the 3 numbers. Again, normally these would be 32-bit or 64-bit, but for simplicity reasons, I'm showing them in 16 bits. So at the trie will look like this, and I'll go through at each level. So at the root node, we're going to examine the first digit position, the first bit. And again, it's one way, it's 1 bit, so it's either 0 or 1. So in this first position, all 3 keys have the bit set to 0. So at bit 0, I have a path going down. At bit 1, it's null, because there's no key that matches that. Then I go down to the second level. And for simplicity reasons, we're just going to repeat this. Think of this repeating across 10 times. Right? But it's going to be the same thing. I have a 0. All my tuples or keys have a 0. at every single position and have a path going down, and 1 doesn't have anything. But now when I get to this position here, now I see that there's a difference. So for key 10, its bit at this position is 0, so there's a path going down to this side. For the other two, it's 1, so there's a path going down here. So now if I look at, say, the remaining part of this key, again, it's a single path going down, and it's, it's 1, 0, 1, 0, and same thing. If it's null, there's no, the bit is not set at that position, it's null, otherwise it's a path going down. And then the leaf node, again, this is just a record ID that points to the corresponding tuple. Same thing for the other side, right? At this point here, they're the same, but then they split here, and then now I have separate paths for the other parts. Right? Is this what, so we can do this in 1 bit, 2 bits, 8 bits, 16 bits. We can do this at different levels, different granularities. So what's one simple optimization we can do for this? There's actually 2 optimizations. How can we reduce the size of this trie? Yes?
We definitely don't need to use space to mark those zeros and ones.
Exactly. So he says we don't need spaces to mark zeros and ones because what is this saying, right? So again, this is the value at the digit, this position, and then here's the pointer for it. So this is redundant. So all I really need to do is just store the pointers, right? Because if the bit is set to 0, I want offset 0. If the bit is set to 1, I go to offset 1. So this is horizontal compression. This is reducing the size of the each trie node. What's another compression way I could compress this in the back? He says repeating the number 0 10 times. For this one, you actually have to have. So once I get down here, these parts here, there's no other key that matches this. It's sort of what he was saying, but up here, the reason why we had to keep this is because we're going to split here, so we need to know how we got down to here. So, but after this, we don't need to store anything. We instead can just store, well, if you go down here at this position, at this level, if the bit is 0, I only have 1 key that matches, so let me just store the tuple pointer to that key. And then same thing over here. So this is vertical compression. Yes?
Do you have to store it in order? Can't you just put in each level a little marcation as to what digit of the thing you're searching for it is, and you just check that, so you don't have to go in order, so you can have a more balanced tree?
So your question is, instead of storing the what? Sorry.
So the top node, right?
Yes.
The 0 bit.
Yes.
The first bit. Can't you just put a little number in each level that says which bit you are, and you can go in a different order? Instead of just going iterating from left to right, you could go from second and fifth or something like that to get more balanced tree.
So this is a little market optimization. There's CPU instructions that you can run in a single instruction for a bit map, a bit sequence. Find me the value at this offset in a single instruction, so you don't have to iterate.
Okay.
Or you count me the number of ones in this bit field, right? There's CPU instructions to make this go really fast. So it's not like you're just doing in a for loop sequentially scanning over this. It's not as bad as you think it is. Okay, so again, this is low-level bit information, but it's showing you at the extreme case, you wouldn't actually want to use a one bit trie. Usually, you want to store them as 8 bits or a single byte. But to me, this is the easiest way to understand this. And so even now, if it's 8 bits, same thing for every single position. I just have a pointer or not, and I can quickly jump to the one, the offset that I want. So this is fine and dandy if everything's static, but actually, how do we modify this thing if we do inserts and updates and deletes? So there is no standard way to maintain a trie in the way that there was for a B+ tree. Different implementations do different things. So I'm going to show you one brief example. I'm not saying this is the only way to do this, but there's some of the things you have to be mindful if you're actually trying to build one. So let's say, again, this is the hello, hat, and have key set we had before. So I insert here. Again, I traverse down. I would find this slot here, and now I can insert this into this, right? So now let's say I want to delete hat. Well, that's here. I go ahead and delete that. And rather than reshuffling everything, maybe it's okay for me to leave an empty space here, right? Because then I don't do any compaction. But now let's say I delete have, and now I remove this, and I say, well, now I have this node here by itself. And so if I want to actually find hair, I'd have to do an extra hop to go down to the IR, but I know I'm not going to have any other match. So you could decide just to roll everything up and put it up here. Different implementations do different things. If you take the advanced class, we'll cover a bunch of these things. Yes?
So once we do the compressions to the try, we get radix tree? Like that's
Yeah, so yeah, let me be real clear. A radix tree is one that's vertically compressed. Yeah, I should have labeled that more carefully. Yeah, I don't have the slide. Yeah, a radix tree is one where you remove all the paths. Yeah, I apologize. I don't know what. I don't know. It used to be a slide here to define what a radix tree. I don't know what happened to it. Sorry. Oh no, this is it. Sorry, this is the radix tree. Sorry. It's when you do the vertical compression to remove any nodes where there's no other differentiating path below it. Sometimes it's called a Patricia tree, but usually they're called radix trees. And again, it's a subset of a trie. Okay. So we covered modifications. And the last thing I want to briefly talk about is actually how we do comparisons. Actually, in the sake of time, I'm going to skip that. The last thing I want to talk about is inverted indexes. Again, tries are super interesting. No commercial data system, as far as I know, supports them out of the box. Hyper is a system out of from Germany that Tableau bought that runs in Tableau's. It's Postgres compatible. They're all in on try. We've done some research here on tries. They're super interesting. But right now the B+ tree is still the dominant data structure everyone uses. But there's a lot of interest in them. All right. So real quickly, everything that we talked about so far for these indexes have been satisfying or handling index or point queries and range queries. So if I want to find a record where it's people that live in zip code 15217, right, that's an equality predicate to find exactly the thing I'm looking for. Or if I'm trying to find things within date ranges, right, that's a range scan. Again, I can use a B+ tree for that. Where the B+ tree and the hash tables are not good for is when we want to do keyword searches. So for example, say I have the entire corpus of Wikipedia. I'm going to find all the Wikipedia articles that contain the keyword Pablo. I can't use a hash table index for that, and I can't use a B+ tree index for that, because I'm trying to find a sub-element of a value for an attribute, right? And again, for the B+ tree, and I have to have the exact key. I can't do a partial key. I can do a partial key lookup if the key is comprised of multiple attributes, but within single attribute, I have to have the entire value of it. I can't have like the first 16 bits. So this is the problem we're trying to solve here. So quickly, just remind everyone what Wikipedia looks like. The main thing we care about is that there's this revisions table that has a text. That's my bookie. Sorry, that has the text field. All right, and we want to be able to find all the matches for Pablo for this. So if I try to create an index on the content field, this is going to be a really bad idea, because again, it's going to take the entire key or the entire contents of this attribute in our table and try to build a B+ tree on that, right? And in case of Wikipedia, this would be really stupid because some articles can be kilobytes, and now I'm storing the entire key in my index, and the only thing I can do lookups on is if someone gives me the entire article back, which is stupid, right? And so in order to do this kind of lookup like this, I want to do instead of something equals something, I want to do a keyword search like with a like clause with wildcards and say find me all the matches where the keyword Pablo is inside of it. And this is actually not even the right SQL we want either way, because this is going to match for things that have Pablo as a prefix, like Pavlov, like the famous Russian scientist. And I'm going to find exactly where my name is being used. So this predicate itself is not going to be useful for us. So this is what an inverted index does for us. So an inverted index is going to map words, words as we describe them in the English language or in natural languages, not like byte sequences in the processor. It's going to map words to the records that contain them. And then it's going to allow us to then do lookups on this index and say, find me all the records that contain this keyword or have this keyword of this certain property. So these are sometimes called full text search indexes. And just like with when I created the index and I told Postgres I wanted this thing to be a hash table index, you can do the same thing in some databases. You can say, I want to create an index and I want it to be an inverted index or a full text search index. So sometimes in the theoretical literature, these are called accordances. And this is because there was this old lady in the 1800s who sat down for 16 years and built an inverted index that mapped every single word used by Shakespeare in his entire body of work. Right? But this is, nobody calls them this. Everyone instead calls them full text search indexes or inverted indexes. So all the major database systems will support some variant of this internally. As I say, when you call create index, you can say, I want to have a full text search index. And they all vary in the sophistication of the indexes and what kind of queries you can run on them. There's also a bunch of specialized database systems that are sold or marketed as full text search databases. So the most famous one is probably Elasticsearch, and this is built on top of Lucene. Lucene is like a library written by the guy that invented Hadoop that does does the search and does the indexing, and then Elasticsearch provides like a server interface to that index. Solr also uses Lucene. I think Sphinx does as well. I use Zapier, which is like a standalone C library that does full text search indexing, because this is better than the MySQL full text search indexing. But ideally, these would be external to like Postgres and MySQL, whereas these other guys are sort of like it's built inside of the system itself. So we're not going to have time to discuss implementations, but basically all the hash table index stuff we talked about so far in the B+ trees, that's what you're going to use to build one of these full text search indexes. So the thing that does a lookup and find me all the records that have contained this word, I could build that as a hash table. I could build that as a B+ tree, but I'm going to augment it with additional metadata that provide the context about how that word was being used in the tuple. So the kind of queries you can do that you can't do on a B+ tree in a full or inverted index, you can do phrase searches. So I can do, again, find all the records that contain the word Pavlo. I can do proximity searches, so find me all the records where the word Pavlo is in, within 5 words or 3 words from, criminal or alcoholic or something like that, right? Because I'm maintaining the context information about how that word was being used. Then I can also do wildcard searches. It's more complicated than the light stuff. I can do regular expressions or complex pattern matching to find things I'm looking for. So the things we do care about slightly is that how we're actually going to build this thing. And again, the different systems will all do different things. The thing they're going to vary the most on is what they're actually storing. Again, this is the context information about how the word was found in the attribute. So at the very simplest form, you just have the word itself and then map to a record ID. But I can also include what other words are around it, how many steps away from other words, and that will determine how complex queries I can support on this. The other tricky thing is actually when do you update these things. So if it's built inside of the system, you could, in theory, on every update, make sure you update your search index or inverted index. If it's external, then you have to run this as a cron job or push updates to it. A lot of times, people will stage updates in batches and then apply them every so often, because potentially updating the inverted index is super expensive. And again, I realize I'm going over this super fast. I just want you to be aware that beyond B+ trees and hash tables that we talked about here, there's a whole bunch of other database indexes that are available that can do things beyond point queries and range queries that we've looked at. And actually, the other class of indexes that we didn't talk about are the geospatial tree indexes. So things like R trees, quad trees, KD trees. These allows you to do multi-dimensional lookups, like in your geometric spaces and things like that. These are very common now in like video databases and image databases. So there's a whole class that Christos Faludis, the other database professor, teaches, 15826. He teaches it in the fall and spring now. So if you're interested in this kind of stuff, he'll be teaching it in the spring. So the main takeaway for all of this is that most of the time, the B+ tree is going to be what we want. That's the go-to index that's resilient and solves many of the problems that people have in databases. Inverted indexes, we can go. You want to go more detailed? There's a whole other class in LTI 442 or 642. I think it's called search engines, right? But in a search engine, underneath the covers is basically an inverted index. So it's the same technology, the same methods. Okay. All right. So next Wednesday, we're now going to go look at how we actually make our B+ tree thread safe. So we've sort of washed all over this, or we've not talked about it, avoid the problem of how do we allow multiple threads to update the index at the same time. So now we're going to spend more time talking about that. The thing we need to talk about now is that we spent the last 3 classes talking about data structures. We spent a day on hash tables and spent 2 days on B+ trees, radix trees, and other tree data structures. So for the most part, during this entire conversation, when we talk about these data structures, we've assumed that they were only being accessed by a single thread. There was only one thread that could be reading and writing data to the data structure at a time. And that simplified the discussion so that you just understand what's the core essence of how these data structures work. But in a real system, we obviously don't want to just have a single thread be only accessing the data structure at a time. We want to allow multiple threads. Because on modern CPUs, there's a lot of CPU cores, so therefore we can have multiple threads running queries and all updating our data structures. We're also going to allow this to hide disk stalls due to or stalls due to having to go read things from disk, because now if one thread is doing something and it reads a page that's not in memory, it has to get stalled while the buffer pool manager brings that in, and then we can let other threads keep running at the same time. So we're going to have a lot of threads running in our system, and we do this because that maximizes parallelism or reduces the latency for the queries we want to execute. So for today, we're now talking about it. Now we bring back multiple threads and want to update and access our data structure. What do we need to do to protect ourselves? So I'll just say as a quick aside, so everything that we'll talk about today is how most database systems actually work. Most database systems that support multiple threads will do the things that we're talking about today, doing this latching stuff. There are some particular systems that actually don't do any of this and only allow single threads to still access the data structures, and they still get really good performance. So VoltDB and Redis are probably the two most famous ones that do this. So in case of Redis only runs in one thread. It's a one-threaded engine. In VoltDB, it's a multi-threaded engine, but they partition the database in such a way that every B+ tree can only be accessed by a single thread. So you avoid all this latching stuff that we're talking about today, and you get really great performance, but obviously this means that it complicates scaling up to multiple cores or multiple machines. But again, we'll talk about these things later on in the semester, but the main idea now is that everybody pretty much does the things that we're talking about. So the way we're going to protect our data structures is through a concurrency control protocol, a concurrency control scheme. And this is just the method in which the database system guarantees the correctness of the data structure by enforcing all the threads to access the data structure using a certain protocol or a certain way. And so I'm putting the word correct in quotes because that can mean different things. And the kind of things we're talking about they're accessing, although we've been focusing on data structures, but it really could be for any sort of shared object in the system. Right? It could be for a tuple, it could be for an index, it could be for the page table in the buffer pool. It doesn't matter. So the two types of correctness we care about in concurrency control are logical correctness and physical correctness. So logical correctness would be like a high-level thing that says, if I'm accessing the data structure, am I seeing the values or am I seeing the things that I expect to see? So if I have a B+ tree index, I insert the key 5 in my thread. If that thread comes back and reads key 5 right away, it should see it, right? Should not get a false negative. Right? That's a logical correctness thing, that I'm seeing the things that I expect to see. The thing that we're going to care about in this class is physical correctness. How do we protect the internal representation of the data structure, how it maintains pointers and references to other pages and keys and values? How do we make sure that as threads are reading and writing this data, that the integrity of the data structure is sound? So an example would be, we don't want the case where we're falling down, traversing to the B+ tree, and when we jump to the next node, we have a pointer to that, and then by the time we read the pointer, figure out where we need to go, and then try to jump there, somebody else modifies the data structure where now that pointer is pointing to an invalid memory location, and we would get a seg fault. So this is what we're trying to do today. We're trying to protect the internal data structure to allow multiple threads read and write to it, and that they still, the data structure is behaving correctly. For the logical correctness, we'll worry about this more when we talk about transactions and concurrency control. Right? This is a whole other super interesting topic. But for today, we're saying, how can we make sure that the data structures are thread safe? So we'll begin by talking about what is actually a latch, go a bit more detail than we talked about so far, and how it's actually implemented. And then we'll start off with an easy case of actually doing thread safe hash tables, using latches for those, because they're actually really simple to do. But then we'll spend most of our time talking about how to handle this in B+ trees, and we'll talk about how to do leaf node scans and other optimizations, again, when we have multiple threads accessing things at the same time. Okay? All right, so I showed this slide last time And I don't think everyone, we only talked about it very briefly, and I don't think everyone absorbed it. So I want to spend more time talking about the difference between locks and latches. So in the database world, where I live, a lock is a higher level concept that protects the logical contents of a database. So a logical content would be like a tuple, or a set of tuples, or a table, a database. And we're using these locks to protect these logical objects from other transactions that are running at the same time. Like if I'm modifying something in a transaction, and I don't want anybody else to modify that tuple at the same time that I am. Right? You may, for other reasons, but for our purposes, assume that we don't want that to happen. So for these locks, we're going to hold them for the entire duration of the transaction. Again, that's not entirely true, but again, for our purposes, just assume that's the case. And then we need to be able to roll back any changes we make to the objects we modify if we hold the locks for them. So if I'm trying to transfer money from my account to her account, if I take the money out of my account and then I crash before I put the money in her account, when I come back, I want to reverse that change I made to my tuple. So that means the data system is responsible for knowing how to roll back these changes. So notice up here, I didn't say anything about threads. Right? I'm talking about transactions. So a single transaction could be broken across multiple threads, and they could all be updating the same tuple. That's okay. That's allowed because the transaction holds the lock. It doesn't matter what thread that's actually doing the modification. Where we get now into the low-level constructs that we care about, again, protecting the physical integrity of our data structures or the objects, is latches. So in the operating system world, this is what they call locks or mutexes. In our world, there's latches because we need to distinguish them from locks. So latches are going to protect the critical sections of the database system's internal data structures from other threads that are reading and writing to that data structure or that object at the same time. So we're only holding the latch for a short period, just for the duration that we're in the critical section to do whatever operation that we need to do. I want to update a page, I hold the latch on that page, make the change, and then release the latch. We don't need to be able to roll back any changes here because the operations we're trying to do are essentially meant to be atomic. So I grab the latch on something, I make whatever change I want, and then when I release the latch, then the operation is considered done. So all the changes are there. If I can't acquire the latch, then I'm not going to do the operation anyway, so there's nothing to roll back. So another way to think about this is this great table from that B+G book I recommended a few lectures ago from Gertz Graphy. We has this nice table that lays out, again, the distinction between locks and latches. So for locks, we're going to separate user transactions from each other, and they're going to be protecting the database contents, tuples, tables, things like that. And we're going to hold them for the entire duration of the transaction. There's going to be a bunch of different lock types that we can hold on these objects. Again, we'll cover this in a few more lectures. And then when it comes time to actually dealing with deadlocks, we're going to rely on some external coordinator, a lock manager or transaction manager, to resolve any deadlocks that could occur. And the methods we can use are waits for timeouts, aborts, and other things. Again, we'll focus on these later. What we care about is over here. We have these latches that are going to protect threads from each other for our in-memory data structures. We're going to protect the critical sections inside these data structures. There's only going to be two lock modes, read and write. And the way we're going to avoid deadlocks is through us being good programmers, which is nice for databases. Good equals expensive, right? So it's up for us to make sure that we write high-quality code in our data structures to avoid deadlocks, because there is no external thing like a transaction manager or lock manager that's going to rescue us if we have a deadlock. It's up for us to design and implement our data structure in such a way that deadlocks cannot occur. And we'll see what that looks like later on. So again, our focus is on here. We'll discuss all this lock stuff in lecture 17 after the midterm. Again, I find all this super fascinating, but this is like one of the black arts of database systems, if you can actually make this stuff work. All right, so let's talk about the latch modes that we can have. Again, there's only two modes, read and write. So if a latch is being held in read mode, then multiple threads are allowed to share that read latch, right? Because again, it's a read-only operation, so I can have multiple threads read the data structure at the same time. There's no conflict, there's no integrity issues that could occur, so they can all share that. If I take the latch in write mode, then I can only, that's an exclusive latch, only one thread can hold that latch in that mode at a time. So if I hold the write latch, I'm making changes, nobody else can read that object that I'm protecting until I finish. Right? That's the only two modes we care about. Think of this as like, again, multiple threads can share this one. This is an exclusive latch. All right, so let's talk actually how you implement a latch in a real system. So the first approach is probably the one you're most familiar with, when you take any kind of systems course or operating system course, is a blocking operating system mutex, a blocking OS mutex. So this is the simplest thing to use because it's sort of built into the language. Like in C++, the standard template library has this thing std mutex, and it's really simple to use. You just declare it, then you call lock, do something on the object you're protecting with it, and then you call unlock, and you're done. Right? So does anybody know how this actually works in the operating system, at least in Linux? How does a mutex like this work? Yes. He says futex. What is a futex? What's that?
Memory, special memory.
He said, well, so he said futex. He's correct in Linux. Futex stands for fast user space mutex. The way it works is that there is in user space, in the address space of your process, there'll be a memory location that has, like a bit, it's usually a byte or so, but it'll have a memory location that you can then try to do a compare and swap on to acquire that latch. But then what happens is if you don't acquire it, then you fall back to the slower default mutex where that goes down into the operating system. So the idea is you do a quick compare and swap in user space. If you acquire it, you're done. If you don't acquire it, then you fall down to the OS, which is going to be slower. Because what happens is if you go down to the OS and sit on mutex inside of the kernel, then the OS says, aha, well, I know you're blocked on this mutex. You can't get it. So let me tell the scheduler to deschedule you so you don't actually run. And the reason why this is expensive is because now the OS has its own internal data structures that is protecting with latches. So you got to go update now the scheduling table to say this processor, this thread can't run yet. So he's correct. Fast user space mutex will be fast because that's just a spin latch. We'll talk about in the next slide. But if you fall down to the OS, then you're screwed. So this is another good example where like we were trying to avoid the OS as much as possible. For the first project, you guys use this because it's fine. But if you have a high contention system, then everybody's going down to the OS, and that's going to be problematic. So the alternative is to implement it ourselves using a spin latch or test and set spin latch. So this is extremely efficient. It's super fast because on modern CPUs, there's a single instruction. There's an instruction to do a single compare and swap on a memory address. We think of this like I check to see whether the value of this memory address is what I think it is. And if it is, then I'm allowed to change it to my new value. So think of like the latch is set to 0. I check to see whether it's 0. And if it is, then I set it to 1. And that means I've acquired the latch. And you can do that on modern CPUs in a single instruction. Right? You don't have to write C code like if this, then that. It does it all for you. So the way you would implement this is in C++ is that you have this atomic keyword, which is templated. You can put whatever you want in there. But they have a shortcut for you called atomic flag, which is just an alias for atomic bool. And so inside this, now when we want to acquire this latch, we have to have this while loop that says test and set the latch. If I acquire it, then I jump out of the while loop, and because I hold the latch. If I don't, fall into the while loop, and now we have to have some logic to figure out what should we do. The simplest thing is just to say, all right, let me just retry again, loop back around, and keep trying it. Right? The problem with that is, though, that's just me burning out your CPU. You're not burning out literally, but you're just burning cycles in your CPU because you just keep trying to test and set, test and set, test and set, and it's always going to fail, and you just keep spinning around in this infinite loop. So the OS thinks you're actually doing useful work because it doesn't know what instructions you're executing. So it says you keep executing instructions. Let me keep scheduling you, and you're just spike the CPU. So this test and set thing is the same thing he said before about the fast user mutex. This is the same thing the OS provides you in the Linux standard or the std mutex on Linux. But maybe I don't want to burn my cycles, but just keep retrying. Maybe I want to yield back to the OS, get descheduled, and let it schedule some other thread. Or maybe I try 1,000 times and I'm not going to get this, and I just abort. So this is a good example of where we, as the database systems developers, we can be smart, or we can tune our implementation of how we're using latches in our data structures to be mindful or try to accommodate what we think the workload is going to look like. If I think that this latch is going to be, like whatever the operation I'm doing, the latch is going to be super fast, then it's probably faster for me to just keep retrying because whoever holds the latch will give it up real quickly. But if I think the operation is going to be super long, then maybe I want to yield or for some amount of time or eventually abort. We can't do this in the blocking OS mutex. As soon as we try to get it, we can't get it. The OS takes over and we're blocked. Yes?
So those parameters, are those just some flags? Or
The question is, what is this?
the parameters there?
This?
Like test and set.
Oh, this? Yeah, like the parameters would be like, it's compare and swap. It says, at this memory address, check to see whether the value is this, like pass in a 0. If it equals 0, then set it to 1. Right? And then there's different APIs. Sometimes you'll get back the old value, you'll get back a true whether it's succeeded. There's a bunch of different things. And then they have tests and sets for, for all the different types you could be based on. So again, the main takeaway here is that, again, we in the data system can do a better job than the OS because we would know in what context we'd be using this latch. So for these two examples, though, the latch has just been, do I hold it or not? But as I said before, we have different modes, so we need a reader-writer latch that can support these different modes. And so the way we basically do this is we build on top of whatever our basic latching primitive we have, either the spin latch or the OS mutex, and then we manage different queues to keep track of how many threads are waiting to acquire the different types of latches. Right? So maybe just maintain some counters to say, here's the number of threads that hold the latch in this mode, and here's the number of threads that are waiting for it. So if a read thread shows up and says, I want to get the read latch, well, I look over here and say, nobody holds the right latch, and nobody is waiting for it, so I go ahead and hand it out, and I update my counter to say I have one thread that holds this latch. Another thread comes along, it wants to also acquire the read latch. Again, read latches are compatible, or they can be shared. So we can just recognize that this guy already holds the read latch, so this guy can also acquire it, and we just update our counter. So now the writer thread comes along, wants the write latch. It has to stall because the read latch is being held by other threads, and so we just add our counter here to say that we're waiting for this. So now, if a read thread comes along and wants the read latch, what should happen?
I mean, it depends upon what policy we are using.
Right. So he says it depends on what policy we're using. We could just immediately say, oh, well, the read latch is already being held. Go ahead and also acquire it. But that could lead to starvation because the right thread will never get to it. So in this example here, we could just stall it, add it to our counter, say we're waiting for this, and then eventually when the first two guys release the latches, the writer thread will get the latch. Again, this depends, what policy we want to use depends on in what context the latch is being used. Right? If it's a data structure where there's not many writes, but the writes are really important, then we want to give higher priority to the writer threads. Okay? And again, we just build on top of our the data structures or the latching primitives that I showed before to implement something like this. And you can still do this. You can still, depending on how you organize the memory, you can still do this. Most of the operations on this atomically. Okay. All right. So let's now see how we take these latches and actually do something with them. So the first one, as I said, we'll first talk about do hash tables because this is actually super easy to do. And the reason why it's super easy to do is because the ways in which threads can interact with our hash table is limited. Meaning we probe into for this one, assuming we're doing like the static hashing table, the extendable and linear stuff, the dynamic ones, they're a bit more complicated, but the same principles apply here. But say in the linear probing hashing table, my key shows up, I just hash it, I jump to some slot, and then I just scan down in sequential order on the hash table till I find the thing what I'm looking for. And every other thread is doing the same thing. They're always scanning top to bottom. Eventually you reach the bottom and loop back around, but you think of that as just a circular buffer where you're essentially always scanning down. So in this case here, deadlocks aren't possible because everybody is going in the same direction. Nobody's coming up in the other way, and they hold a latch that I want, and it holds a latch that I want. Like you can't have a deadlock. So this makes it super simple. So for now, to resize the table, This one, we just take a global latch usually in the header page that just prevents anybody else from reading and writing the table until I complete the resizing. But again, that's if we size our table large enough in the very beginning, like this is a rare occurrence. Most of the time we're just doing probes or insertions, and that'll be fast. Deletions also complicate this too if you want to do compaction or move data around, but for that we can just ignore. So the two approaches to do this will differ on the granularity of the latches. So the first approach, you just have on each page, you just have a single reader-writer latch. And so when a thread wants to do something, do a lookup, before it can read the page or access it, it has to acquire the right latch for that page. The other approach is to do more fine-grained latching, where you have a latch for every single slot. So that means as you're scanning down, you acquire the next slot's latch, and then you can go into it and then look for whatever you're looking for. So there's this trade-off between the computational and storage overhead between these two approaches, because the page latch, we have to store less latches. There's only one per page, but now this can potentially reduce our parallelism because I can't have two, even though two threads might be operating in different slots, because it's in the same page, they can't run at the same time. In the case of having a latch per slot, it's going to allow for more parallelism because the latches are more fine-grained, but now I'm storing more latches in every single slot, and now it's also more expensive to keep acquiring all these latches as I'm scanning through, because I'm doing it for every single slot that I'm looking at. So let's look at some high-level example. So the first one would be page latches. So again, say we have a simple three-page table that has 2 slots per page. And so the first thread wants to find D, and say D hashes to this position here, this slot. So before I can go look inside of it to see whether the thing I want is there, I first have to get the read latch on it. And then once I have that, now my cursor can start looking at it. Now let's say another thread comes along and they want to insert E, and E wants to hash to where C is. Can it do that? Can it actually start looking at it? No, right? Because it wants to take a write latch on this page because it doesn't know that C is full. It doesn't know it's going to have to scan. But so before it can even look at it, it needs the write latch. The write latch is not compatible with the read latch, so it has to stall and wait. So the first guy scans down, he looks at C, and now he needs to go look at this next page here. And again, the way we figure out what page to look at is we just look, we look in our the header for the hash table, and the header is going to say, here's all the pages that you're looking for. But logically, they're ordered sequentially, right? So like page 0, page 1, page 2. So you look in the header and say, where do I find page 2 for my hash table? And so in order to do this traversal, when I want to go from page 1 to page 2, I actually don't need to hold the latch on 1 in order for me to jump down to 2. Because my hash table is static, I'm not resizing, so this location is always going to be the same. So I can immediately release the latch before I jump to this and allow anybody else to keep running, and then I can go ahead and acquire the latch for this. This is going to be different when we talk about B+ trees. B+ trees, you have to hold the latch on whatever node you're coming from before you jump to the next node. And it's only when you get to the next node do you then release the one behind you. Yes?
So whenever the second thread goes to access, can it obtain a read latch to read through and figure out, maybe it doesn't even need to look at 1 yet, it can jump to 2 and skip over the
Yeah. So he proposed an optimization where, in this case here, for thread 2, instead of trying to require a write latch, could I just require a read latch, figure out whether the thing I actually want would be there or not, and then if it is, then I go back and try to acquire the write latch, or I just jump down here and say, do the same thing because I know the thing I'm looking for is not here. If there's no deletes and no movement, yes. We'll talk. The same technique will be applied for B+ trees. I'm doing it the naive way, but yes, you can absolutely do that. In general, you don't really do latch upgrades. You can't say I'm in read mode now, put me in write mode. You release the latch and then in one mode and get acquired again in another mode. All right, so this guy has the read latch. He can start reading this. Now this guy gets the write latch. It sees that C is not what it wants, so it wants to scan down here. And this time T1 has gone away, so we can go ahead and do the write latch. See that this slot's occupied. Come down here and do the insert. Again, it's more coarse-grained because only one thread can be inside. If they're doing, if the latch modes conflict, there's only one thread at a time could be inside the table. but it makes it more simple to actually acquire these latches. I'm not acquiring latches every single one. So let's see how to do it in with slot latches. So again, T1 starts, it wants to do find D, it hashes to where A is, so it acquires the read latch on A, and then T2 starts, it wants to do a write, so acquires the write latch on C, and at this point, when T1 starts up again and tries to look at this, it can't run because it can't get that latch, so it has to stall, whereas this other thread can keep going down here. And then now this guy can then pick up and keep going behind it. Right, so then eventually it has to stall too because it can't go here. This guy moves on, does his insert, and then this guy can then proceed. Right, so we can do the exact same optimization that he said, and we'll see this in the context of B plus tree. I could just keep seeking read latches till I find the spot that I want, and then I try to acquire the read latch that I want. But I do have to handle the case where I take the read latch, see this is the spot I want to go, then I release the read latch, then come back and try to take the write latch, and in between that time, somebody might have inserted something in my slot, and then I need to be able to handle that and keep scanning down below. So that technique works, but there's extra stuff you have to do. So again, the main takeaway I want you to get from all this, there can't be a deadlock because everyone's scanning from the top to the bottom. That makes our life easier. There's nobody else coming in the other direction. So that's why also too, we can just release the latches before we jump to the next one because we're not worried about the location of the page we're jumping to changing. Okay? All right, so let's talk about more complicated things. Let's talk about how to do this in a B plus tree. So again, we want to have multiple threads running at the same time, and then we allow them to do reads and writes without having to lock or latch the entire tree during that duration of the operation. So the two things we need to handle in our B plus tree to make them thread safe is that we need to handle the case where two threads are trying to modify the same node at the same time. And then we need to handle the case where one thread might be traversing the tree, and then down below it, before it gets to the leaf node, another thread does a modification that causes a split and a merge, and now the location of a page may end up, or of a node may end up getting moved around, and the data I'm looking for is not there. Or in worst case scenario, I have a pointer to now an invalid memory location. So let's look at a high-level example here. So we're going to focus on this side of the tree. I'm just labeling them A, B, C, D, E, and then so forth on the leaf nodes. So say we want to do a delete on 44, down to the bottom. So the first thread is going to start at the top. Again, we just do the traversal we talked about so far, where we look at the separator keys, we figure out whether we want to go left and right, and we move down to the child node based on that. So then we need to get down to this leaf node here, and we can go ahead and delete our entry. But now we see that our node is less than half full. In this case, it's entirely empty. So therefore, we have to rebalance. And so we're going to want to, in this case here, instead of doing a merge, we'll just copy over a key from one of our siblings. But let's say before we can do that rebalancing, the OS swaps out our thread, and we get stalled, and now another thread is start running. And that other thread wants to do a lookup to find key 41. Right down here at the bottom. So it does the same thing. It starts traversing the tree, and then it gets down to this point here, and it looks at the separator keys and figures out, oh, I want to go to this node. But then the OS stalls this, switches back to our first thread, and the first thread moves 41 over. And then now when my other thread starts up running again, I get down here, and the thing that I thought was there is no longer there. Right? So best case scenario, this is just, we got a false negative here. We thought key 41 does exist, but the index told us it didn't exist. That, of all the anomalies or issues we're talking about today, that's the best case scenario. Worst case scenario was this node got moved around, and then now this pointer pointed to nothing. And we would get a seg fault, and our program would crash. So the way we're going to handle this is the classic technique called latch crabbing or latch coupling. When I was a young lad, when I was taught databases, I was told the term was called latch crabbing. I don't know what the textbook actually uses, but the Wikipedia, I think, calls it latch coupling. It's all the same concept, same thing. So latch crabbing is a technique that allows multiple threads to access the B plus tree at the same time, and we're going to protect things using latches. So the basic idea of the way this works is that anytime we're at a node, we have to have a latch on that node. It could be in write mode or read mode. And then before we can jump to our child, we got to get the latch on our child, the next node we're gonna go to. And then when we land on that child, we can then examine its contents. And if we determine that the child node we just moved to is safe, then it's okay for us to release the latch on our parent. And so the term latch crabbing sort of has to do with the way like crabs walk, like moving one leg past another. That's how we're going to acquire latches as we go down. So our definition of safe is one where if we're doing a modification, the node we're sitting at will not have to do a split or merge no matter what happens below it in the tree. So that means that it's either not completely full. If we're trying to do an insert, we have room to accommodate any key that may come up to us or any key that we're inserting. And then if we're doing a delete, we know that it's more than half full. Meaning if we have to delete a key, we're not going to have to do a merge. Right, so again, the basic protocol works like this. At the very root, you acquire the right latch you need. So in the case we're doing a find, it's all read latches all the way down. Again, every single time we get to the next node, we release the latch on our parent node where we came from. Because again, we're not making any modifications, so every node is deemed safe. For inserts and deletes, we start off with getting right latches all the way down, and then as soon as we recognize that the node we're at is considered safe, we can release any right latch we have up above in the tree. Because again, no matter what happens below us, they will not be affected. They will not have to get changed. So let's look at some examples. So again, find is super simple. I want to find key 38 at the bottom. So my thread starts off the beginning. I get the read latch on A. I come down to now B. And now at this point here, again, because it's a read-only operation, it's a find, it's safe for me to release the latch on A. So as soon as I get down to B, I can release the latch on A, and I'm good to go. And now I keep scanning down and do the same thing. Get to D, release on B. Get to H, release on D. And now I do my read, and I'm done. Right? Pretty straightforward. So let's see now if we want to do a delete. So I start off with the right latch on the root. I come down to B after I acquire the right latch. Now at this point here, is it safe for me to release the latch on A? No. Why? Because I only have one key in B. And so I don't know what's below me yet. I'm doing 38, so I'm going down here. I don't know what these other nodes look like yet. So if I do a delete and I have to, or a merge and I have to remove this key, now I have to make a change up to A. So in this case here, we have to hold the latch on B. Or sorry, hold the latch on A. So then we get the latch on D, get down here, and now we recognize that no matter what happens below D, we know that we have room to accommodate, or we can at least delete one key and not have to merge. So we can, at this point here, we can release the latches on A and B. So essentially the thread is just sort of keeping a stack of like, here's all the latches I'm holding as I go down. So it knows at some point when I'm at a safe node, I just release everything up above me. All right, so now I get down to H. I can release the latch on D because H is 100% full. And then I go ahead and do my delete. And then when I'm done, then I release the latch and I go home. So let's see now an insert. Same thing. Start with the right latch on A in the root, go down to B. At this point here, I recognize that B can accommodate any new insertion, so it's safe for me to release the latch on A. So I go ahead and do that. And then I go down to D. D is considered full, so I don't know what's going to happen below me, and so I have to hold the latch on B. So then I get down to I, and now I recognize that I can never split because it has enough room. So before I do the update, I release the latch on B and D. And then I can do my insert. So for this, the order in which you release the latches doesn't matter from a correctness standpoint, right? So going back here, I have to release the latch on D and B. If I release the latch on D before B, that doesn't matter because no one's going to get to D anyway because they can't get through B. So from a correctness standpoint, it doesn't matter. But from a performance standpoint, we obviously want to release this one first, because this covers more leaf nodes. So you want to release the higher up latches as soon as possible. Okay. Let's look at one more example where there could be a split. So I want to insert 25. Same thing, right latch on A, right latch on B. B won't get over full. I can release the latch on A. I come down to C. C is not going to get over full. So I can release the latch on B, but then now I come down to F, and now I see I need to do a split. So in this case here, I need to hold the latch on my parent node on C while I make the change. So I first insert 25 here, take the spillover page over here, put 31 there, and then update my parent node. Do I need to have a latch on this new guy down here? What's that? He says no. Why?
Nobody can access it because you have latch on the parent.
He says nobody can access it because you have a latch on the parent. That assumes that there's no sibling pointers, which we'll talk about in a second. So in this example here, for simplicity reasons, I'm not going to require the latch because everyone's going top to the bottom. If I'm scanning along the leaf nodes, then yes, someone can get to this, and I have to protect it. But we'll get to that. Okay? Yes?
When you said that the threads have a stack of the locks, shouldn't it be a queue because you are saying they should release the
His statement is, I said that the threads have a stack of the latches that they're requiring as they go down. Shouldn't it be a queue? Yes. First in, first out. Okay, yes.
Yeah. When we are talking about locking, we used to say that we release the lock that we first acquire, like release in the reverse order of the acquired locks in like OS.
Yes.
But in releasing the latches, we release the most highest latch, which is the first actually we acquire. So that causes like.
So his statement is, I said, going back to this example here, I said that you want to release the latches from the top to the bottom. Yeah. And you're saying in the OS world, you release them in reverse order. So again, think about what we're doing in the data structure here. At this point here, like no one can get to D unless they go through B. So me releasing the latch on D doesn't do anything because nobody's waiting to get that latch. Somebody up above could be waiting to acquire B. So I want to release that latch as soon as possible. So because we know what the data structure, how it's being used, and we understand the context of how the latches are being used, we want to release this one first. Okay? Okay. So now I want to ask you guys, what was the very first step I did for all those modification examples, for the inserts and deletes? What's the very first step you do?
You latch the root.
Exactly. You latch the root in exclusive mode or write mode. That's problematic, right? Because again, the write latch is exclusive. No other thread can acquire any other latch on that node. So this becomes a single point of contention, a single bottleneck. In order to get into the data structure, everyone has to acquire this write latch, and only one thread can hold that write latch at a time. So this is a big problem. This is going to prevent us from getting high parallelism and high concurrency. So we need something better than just everyone acquiring the write latch as soon as they go in. And so what we're actually going to do is exactly what he proposed before for the hash table, is make an optimistic assumption that most threads are not going to need to do splits or merges at the leaf nodes. So rather than taking write latches all the way down, I take read latches all the way down, and then I take a write latch on the leaf node. If I determine that I don't have to split, then great, I got down with just read latches, and I can make whatever change that I want. If I get it wrong, and I do have to do a split or merge, then I just abort, restart the operation from the beginning, and take write latches down. So this is a standard technique we do in systems where you sort of optimistic versus pessimistic. I'm optimistically going to assume that I'm not going to have to do a split. So therefore, I take the fast path and do read latches. We'll see this in context of other things like for transactions later on. And for most data structures, or most B+ trees in the real world, this is actually a pretty safe assumption, right? In my examples, I'm showing nodes that have 2 keys in them. In a real database system, your node is going to be 8 kilobytes or 16 kilobytes. That's going to have a lot of keys. So most of the operations you're doing are not going to have to do a split and a merge. In the rare case that you do have to do a split and merge, then again, you just fall back to the standard latch crabbing technique that I showed before. So this is from a paper from 1977 from these German guys, Baer and Schlocknick. So there's no name for the algorithm. I think people usually just refer to it as the Baer-Schlocknick algorithm, or optimistic latch crabbing. All right, so let's say again, we want to do that delete on 38. So again, I don't take a write latch from the root. I take a read latch all the way down. And then when I get down to D here, I acquire the write latch on H. I recognize that I'm doing a delete, therefore I'm not going to do a split and merge. So therefore my gamble paid off, and I don't need to restart, right? I can do my delete without having to take right latches, right? Same thing for insert. So insert 25, I take the read latch on the way down. Oops, sorry. I take a read latch and do crabbing all the way down, and then I eventually get to C here, where I take the right latch on F. This one I recognize that I'm going to have to do a split, so I abort the operation and just restart it. Start from the beginning and take right latches all the way down.
Shouldn't you start from the point like where you last released the latches?
So he said, shouldn't you start at the point where you last release the latches on the way down? So that would be, in this case here, C, right?
If like say B had 2 nodes and then C had only 1. In this case, so you have to take on all A, B, and C.
So your question is, so
if B had 2 nodes, then
if B had 2, sorry, what do you mean by 2 nodes? Like 2 siblings? Two keys.
2 keys.
Yeah. Yes.
So then when we come at B, we release A, right?
Correct. Yes.
So then when we go to C, we get C, and then we go to F, we get C and F. So once you restart, you should only get C and F.
But how do you get C and F again?
You maintain a stack of the pointers that you go through, right?
But you can't. He said you can maintain a stack of the pointers where you got down here. I can't do that because, again, say page IDs. Again, these A, B, C, D, E, these are the logical identifiers for these nodes, but they may end up being put into different pages. So because I don't hold any latches on these things, anybody can do anything, and therefore the location of the page ID for these nodes may now be something different. So now it used to be page 1, 2, 3, now it's 4, 5, 6. In my stack, I go look for page 1, 2, 3, and now it's something completely different. Because I can't assume that the location of these nodes will always be the same unless I hold a latch on them. The read latch prevents anybody from writing them and doing any splits. The write latch prevents anybody from else from modifying them. So you always have to restart. Yes?
So it could be possible that initially we thought we needed to do a split, but then we tried to acquire the right locks again. Now
Right latch, but keep going.
Right latches again, and then we saw that we don't need to do that anymore because some process between those 2 steps did something else, right?
So your statement is, say it from the beginning. So if I assume that, yes, just start over, sorry.
We assumed in the beginning that we would need to split, so we acquired the right latch.
Yes.
But then we saw we no longer need to do it now because while we were trying to acquire those right latches, some other thread changed the structure of that.
So your question is, if say we're like, maybe like here. So I hold the read latch on this, and I hold the write latch on this, and then, because at this point I need to modify it, but also I don't know whether someone's going to change something that would cause this thing to get modified as well. Yeah. But again, everyone's going in the same direction, so they can't do that. Like they can't make any change here because I hold the read latch on that. So they can't modify this node, right? Yes?
When you're inserting 25,
yes.
And you get down to the bottom and you hold the, insert 25.
Yeah.
When you get down to the bottom and you hold the red latch on the leaf node.
Yes.
When you want to start from the root, you release this red.
Yeah, the question is, in this example here, when I got down here and took the right latch on F to do the insert, and when I recognized, oh, I got a split, therefore I need the right latch on this, and I don't have it, so I have to restart, do you just hold this the whole time? No.
Then if you're like insert 24 and then insert 25.
Yes.
So when you insert in 24, you get down to the F node.
Yes.
You identify that you need to split, but then the insert of 25 is already as B. So when you release the red lock, and before you get the red lock of the root, the insert 25 comes down to the bottom.
Yes.
And recognize that it also needs to split.
Yes.
So that comes to the situation that he described. The insert 24 will get the red lock and go down through the root and then split F.
Yes.
When the insert 25 comes down, if it's okay.
Yes. So, all right. So rephrase what she said. So say I had this example here. I want to insert 25. I got to the leaf node and recognized, oh, I got a split. Let me restart and take right latches down. But between the time I restarted, somebody else came along and wants to insert 24, and they're going to have the same issue. They also have to split this. So they come back as well and take right latches on the way down. But now, because both of them are taking right latches, only one of them is going to proceed at a time. So now 25, say the guy that wants to insert 25, he gets there first. He inserts this and splits, then 24 is allowed to run. It gets down here, it doesn't care that it already got split. Again, this is a good example between the logical correctness and the logical view and the physical view. I don't care in my index where my key actually exists. So I don't care that like, oh, I try to put it here, so make sure I put it in here the next time, because I couldn't do it the first time. I want to go exactly in this page. You don't care. Every single time you come into it, you're doing this traversal from scratch. You don't care how you got there before. So it doesn't matter that 25 inserts here, it splits, or maybe 24 came first and splits. It doesn't matter. It's still balanced and still correct. Yes?
On the second traversal, we are getting right latches when we don't actually need them.
Correct. So he said the second traversal for 24, it doesn't need a right latch because 25 already split it. Correct. That's more expensive, but what's the alternative, right? The alternative is to take right latches every single time. So optimistic is not perfect. We're not guaranteed to always do the least amount of work we need to do. Because certainly if again, in this case here, my nodes are really small, so I'm splitting a lot, if I'm inserting a lot. So I'd be wasting a lot of cycles, doing wasted work to traverse just to find out I need to come back and take right latches. So in practice, if the contention rate is high and therefore the optimistic assumption is incorrect, you're actually going to be slower than just doing the pessimistic thing. But for these data structures in general, for what we're talking about here, the optimistic one actually works the best. For the hash table stuff, I actually haven't seen numbers. In that case, it's oftentimes the pessimistic approach of taking latches on the page is actually pretty good because it's so simple. For this one, we can be more fine-grained and we get a big win. But it depends on a lot of things. It depends on what the workload is. Are we insert heavy, lookup heavy, delete heavy? It depends on the distribution of our values. It depends on how many cores we have. Right? It varies a lot. In practice, though, most database systems just pick one approach. They don't try to be adaptive because from an engineering standpoint, it's way more complicated. Yes?
We cannot use slot latches in B+tree, right? It's only the pages that we latch.
So he says for B+tree nodes, you can't use the low-level slot latches like you can in a page table. No, because you could be modifying the physical structure of the index itself. So therefore, I'm updating pointers. So like if I have like if I need to do a split and merge, then I need to have latches for all the keys in this node in order to move them around. So in general, you just take a latch the entire page. I think that's true. I could double check that though. It makes things more complicated. Okay. So again, this is just to reiterate what we've already talked about. Again, for the search with the better latching algorithm, same as before. Insert, delete. It's again you take relatches on the way down. If it fails, then you just come back and restart. So again, this is what I was saying before about how we're assuming that most of the time taking the relatches on the way down is going to be good enough. We're not going to have to restart, right? And therefore, if we choose correctly or predict incorrectly, then that first time we went down is just wasted work. We're just burning cycles. And so we're not going to get the better scalability or concurrency we may actually want. But I'll say in practice, this usually works out nicely. All right. So the next thing to talk about is how we actually support leaf node scans. So in the example I've shown so far with the B+ tree, just like in the hash table, all the traversals were in one direction. They always top to the bottom. So there can never be any deadlocks because I never had a thread trying to come up from the bottom to the top in reverse direction and try to hold latches that holds latches that another thread wants, right? So if though now we want to start scanning on leaf nodes, things become more complicated because now we have things coming from top to bottom and also from left to right. And so in this case, deadlocks could occur. So let's see how we handle this. So the first thing I'll say is the original, I said this before, the original B+ tree did not have these sibling pointers on the leaf nodes. This is how most B+ trees have this now, and this comes from the B-link tree that was invented here at CMU. So let's say I have this really simple tree like this, and I have thread 1 wants to find all keys less than 4. So we take a read latch on the root, come down here after we get the read latch on C, we can release the read latch on A, and now we want to start scanning across. Right? So say we reverse order on all the keys in this node, but now we recognize that we got to keep going over here, right? So just like before in the case of crabbing, when we want to go horizontally, we don't release the latch that we hold until we acquire the latch that we want. So in this case here, in order to get the latch on B, I hold the latch on C. Once I acquire it, then I can swing around and then release the latch on C. So in this case here, for all keys less than 4, it's basically keys from less than 4 to negative infinity. So we know that we're going to have to hit the, we want to get to this end of the tree. There's other tricks you can do, like having like fence keys or hint keys, basically to tell you for this node here, what's the keys over on this side here to tell you whether you even need to jump there or not. But for this example, we don't need to worry about that. All right, so let's make it more complicated. Let's say now we have another thread that wants to find all keys greater than 1. Well, okay, that's fine. So both of them start. They both want to acquire the read latch on A. That can happen because that can be shared amongst them. And then this guy gets the read latch on B. This guy gets the read latch on C. That's fine. Then they scan all their keys, and they start going across. And for this point here, B wants the latch on C. C wants the latch on B. That could be shared, right, because they're read latches. So at this point here, they both acquire the alternating ones, the different ones. That's good. Then they slide over, and now they release the latch that they just came from. So because the read latch can be shared, there's no deadlocks. Right? So this works out fine. So let's talk about now when we have writes. So thread 1 wants to delete 4, and thread 2 wants to find all keys greater than 1. So at the very beginning, they start off. They can both get the read latch on A, because we're doing the optimistic latch coupling technique, or latch crabbing, where at my root, I always acquire the read latch and only get the write latch on the child node. So at the very beginning, they both have a read latch. That's fine. And then they both go down here. B gets the read latch thread 2 gets the read latch on B. Thread 1 gets the write latch on C, because that's the entry that it wants to delete. So now let's say that T2 wants to scan across because it's finding all keys greater than 1. So before it can jump into C, it has to get the write latch on C, or sorry, the read latch on C. But it can't do that because the first thread has the write latch on this node. So what should happen? What's that? He says should wait. What else could we do? There's 3 choices, right? We could wait, right? Again, think of that while loop, we just spin in that. We could kill ourselves and just restart the operation. Or it could be like a gangster and try to steal its, go over here, shoot it in the head, take its wallet, take its latch, and then take over. All right, so raise your hand if you think we should wait. 25%. Raise your hand if you think we should just kill ourselves. Even less. Raise your hand if you think we should be a gangster and steal it. Nobody. So, what's the issue here? What does this thread know about this thread? Nothing. Right? Because all the latch is just some bits in the data structure, and then someone acquires it in either read mode or write mode. So there's no global view in the system to tell you what this other thread is doing. The database system at a high level, sure, it says no, I'm doing delete on 4. But at this lowest level inside the data structure, as our threads are traversing through, we don't have access to that information because that would be too expensive for us to go look up. Again, we want these operations to be really fast because we're holding this latch on this guy here, while we're trying to get that other latch. So we could wait, but that could be a bad idea too, because we don't know what this guy's doing, right? We don't know whether, in this case here, in our example, it's just deleting this one record, this one key, and then it's done. But we don't know that. It could also be trying to acquire the latch on B, and therefore I have a deadlock. So the simplest thing turns out to be the best thing is this: we say we don't want to live anymore, and we just abort and kill ourselves, and just restart the operation. Right? This is the fastest thing to do because there's, again, these latches are super dumb. Like there's no information about who's holding them and what they're doing. So rather than try to reason about anything, we just want to immediately stop what we're doing and restart. And assuming by the time we come back, then the latch we wanted is now there. Yes?
How is that better than waiting?
He says, how is it better than waiting? So yeah, you could wait a little bit with a timeout, and then eventually if the latch you want is not available, then you just kill yourself. You could do that as well. But like, I'm talking like maybe wait microseconds.
If you are trying to get a lock on that left side, then won't you already have a right lock on the parent? So there can never be a deadlock. Right?
So his statement is back up here. He said if we're down here on C for thread 1, doesn't thread 1 have a right latch?
If we want to change B also, then he will have a right latch, right? Because he knows that C requires a right latch, so it will go again from the top and get the right latches. And so it will have a right latch on the parent. So in this case, that blue thread can't have a read latch, so there cannot be a deadlock.
So his statement is that if C really wanted to go in this direction and do some modification, wouldn't have to have a right latch up above, and therefore this thread would not have been able to get down here to go across. Well, no, right? So say the blue thread starts first, it gets the read latch, comes down here and gets the read latch that it wants on B, then T1 starts, gets the right latch on A, right? And then gets the right latch on this. So it doesn't know. You don't know this. Like it can come in any order. Yes?
Now, isn't there potential for starvation here, but are we just ignoring that? Like, theoretically, the read could keep on restarting if you have a lot of other.
Yeah. So his statement is, which is true, we could have starvation here, where this thing here says, I can't get what I want. I'm going to kill myself. Tries it again. Same issue. Yes. And there's different ways to handle that. That adds additional overhead. In practice, I don't think MySQL and Postgres do anything. I don't know what the commercial guys. You can do it. You can imagine how to do it. It's extra work, and it may not be worth it. The simple thing might be the best thing. Yes?
What is it restart? Did you restart the whole program? Oh, just the thread.
What do you mean by the whole program?
Like the whole thing?
Like the process? Yeah. Oh, no. Like, it's like, so it's like, like an operation. So this, find all keys greater than 1. We restart that. Okay. Actually, so is that, actually, perfect. The next slide. So the way to think about this is that we have this database system, we have this execution engine that's invoking queries, and it says, oh, in order to get the tuples I need for this query, to answer this query, I got to go to the index and do find all keys greater than 1. So then it invokes that on the index, and then there's basically a retry loop that's inside the index where I keep retrying that to do that operation on that index until it succeeds. For inserts or things that could potentially violate an integrity constraint, yeah, you have a check to say, I tried to insert and I couldn't because it would violate the integrity constraint, not because I couldn't get the latch I wanted. And in that case, you abort that operation. But in general, you just keep retrying this forever, because eventually it'll go through. But to his point, you could lead to starvation or just burning a lot of cycles, trying to traverse the bottom and then try to acquire the latch that you never can acquire. But the main takeaway I want to get out of this is that because there's a potential for deadlock here, but we don't know what the other thread's doing, we want to be super conservative and just kill ourselves immediately. We can wait a little bit, sure, but we don't want to reason about what they're trying to do. We just say we can't get this latch and immediately retry. Because there's nothing else up above that's going to say, oh, there's a deadlock, let me break it by killing one of you. Yes?
Won't it matter the kind of latch the other thread is having?
So the statement is, it wouldn't matter what kind of latch the other thread is having. Sure, yes. In this case here, this guy has a write latch. I can't get the read latch, so that fails.
Yeah, so I was thinking, say, the other thread, T2 has the read latch, then should we kill T1 in that?
Right, so that was the gangster one, right? So that was saying, like, this guy has the read latch. Maybe I prefer reads over writes, and therefore I want to kill this guy. Sure, you can do that, but how do you actually implement that in your code? Now you need a way to interrupt this guy in whatever it's doing to then go steal the latch. That's super hard because, again, we're doing these small critical sections. I don't want to check a global variable that says, did somebody hate me and I should die? Right? So having to coordinate that is just, it's not worth it. In the back, yes?
I have kind of an adjacent question. So in this scenario, if I perform a write on C, and that requires a split on C, which requires me to edit the node anyway, I have to go all the way back up and acquire a write latch on after the read latch is gone.
Okay, so I think you said here, if this thing actually, when I do the delete, I have to merge, and therefore I have to modify the root.
Yeah.
How would that work? Well, again, like I would have to have the right. So when I landed here using optimistic latch crabbing, I would recognize, oh, I'm going to have to merge and modify my parent, so I got to go back and take exclusive latches all the way down. Okay. So that gets handled. Yes.
Can we avoid this issue if we whenever we get a lock, whenever we decide that we're going to not unlock the parent, we just lock all of the children, not just the one we're going to modify. If we're right above a leaf or something like that.
Say it again. So if we're in this situation here.
So we're in this situation here, and let's say we're going to split or whatever.
Yeah.
Right. So we maintain our write latch on A.
Yes.
Right. And we say, okay, we're going to do some operations to require us to modify A. So we just obtain locks on all of the children of A because we know that A is a parent of leaves. And so then we never actually start the read operation on B. And so then we wait for that to finish, and then the read lock starts, and then we never have to worry about this deadlock.
Yeah, so he's actually correct. So this is, what's that?
There will be a deadlock in what he just said. Like say if the blue thread came first, then A is trying to acquire all the children locks, and blue thread is acquiring the lock of that child. So there will be a deadlock.
Right. So, all right, so let me try to distill what you're saying. So if I know I need to do a split in here, and therefore I may have to spill over here, I want to acquire a write latch on this, and then a write latch from all its children, and then that would allow me to do any modifications that I want to do, which includes updating the sibling pointers, which is tricky. And then you're saying that could cause a deadlock because someone could be coming in a different direction.
Yeah,
and
so the blue one already has a lock on B. Now, what he said, you have a lock on A and C, and you want to acquire a lock on B.
Yes.
So now the blue one wants to acquire a lock on C, and he wants to acquire a lock on B. So there will be a deadlock.
Right. So you kill yourself.
So then, if you are killing yourself, then there is no point in acquiring locks on all the siblings, right?
There's no point of acquiring locks. No. So if this guy had a split, I have to update the sibling pointer too. So you do need to acquire a latch on this guy as well. But again, the simplest thing is another thing you can do too, like say two threads at the exact same time to acquire the exact same latches. In practice, there's enough. They're not going to be in absolute lockstep, meaning like if you abort them at the same time, they'll immediately come back and hit the same conflict. They're going to be slightly different from each other. But even then, you could say, all right, I've tried this before and I wasn't able to do it. Let me back off a little bit, and that way I at least come in staggered. Then I avoid that issue. Again, the simplest thing is to say, I didn't get the latch that I wanted, kill myself immediately. And that avoids all deadlocks. And that's going to be different than when we talk about two-phase locking later on for transactions, because we'll have something else can come and resolve deadlocks for us. But we don't have that here. Okay. So the last thing I want to finish up discussing is an additional optimization for handling overflows. And this comes from the B-link. Again, the B-link tree is what first invented the sibling pointers, and then everybody does that now in a B+ tree for the most part, at least in one direction. So normally every time we have to do an overflow, have to do a split in a node, we have to update 3 nodes. We have to update the node being split, we have to create a new node to overflow into, and then we have to update at least one parent or in our ancestry to now accommodate that new separator key for the new node that we added. So the B-link tree guys came with optimization where any single time a leaf node overflows, you actually hold off on updating the parent node so that you don't have to restart the traversal and do the pessimistic write latches all the way down. You just update a little global information table for the tree and says, anytime somebody comes through that part of the tree again, here's how I want you to update it. So let's look at an example. So say I want to insert key 25. Again, I do the optimistic latch crabbing on the way down. I get read latches. I get to here on C. Again, when I get the write latch on F, here's that I would recognize that I'm going to have to split. But then rather than restarting and taking write latches, I just give up the read latch on C. I still do my insert and add the new node. But then rather than having to update this thing, I just have a little global table for the tree that says, if you ever take the write latch on this node C, here's the change I want you to add in, right? And that way, the next time somebody comes through and takes the write latch, they'll do some extra work and finish updating what we wanted. And this is still correct. This is still valid. Because if I come along and now do a lookup on 31, well, I follow the pointers down, and my pointer for all keys greater than 23 will put me here. And now I have to know, all right, well, I actually have this overflow thing. If I'm looking for 31, scan along the leaf node, and that's actually what I'm looking for. Yes?
So the next time there's a write latch on C, so when would that be? Because aren't we doing read latches until then?
Right. So basically, there's again this global thing that anybody can see when they first start. It says, oh, by the way, if you're doing a modification and you're going by C, take a write latch for it. So this guy wants to now insert 33. I can do read latches all the way down to get to B, and then but now for C, I would know, oh, well, I was told that I should take a write latch on this. Let me go ahead and do that. Now I finish the propagation of applying that change there, and then now the tree is considered valid. Right, and take the write latch and complete my operation. So it's like, rather than having to do the restart, you update this thing to say, all right, the next time you go through, somebody else will take care of it for me. Yes?
So how would you usually identify C?
How would you identify C? What do you mean? Like it's a page ID, right? Or a logical node ID. If you're going to see, page 123, by the way, apply this change for me. Yes? Do you update what? Sorry. So back here, yeah. So yeah. Yes. For simplicity reasons, there's different ways to do this. In this case here, if we don't have the same parent, then we may not have a sibling pointer to go in the reverse direction. There's different implementations, but if you want to have bidirectional sibling pointers, yes, you'd have to update that. That makes things way more complicated than what I could show in a class.
And when you get the link from the C to our overflow, you need to update the overflow link as well?
Like this thing?
Yeah.
Well, that's just a sibling pointer. Right, you have to update and say, yes, the sibling pointer, the overflow thing is not there anymore. But it actually doesn't matter anymore, actually. You actually can keep it, right? Because up above, if I'm looking for things greater than or equal to 31, I'm never going to get this node anyway. I'd always get to this one. So you don't actually have to update it. Yes?
So we know that C won't be changed because the first writer to C will update this value, right? Otherwise, like when I previously asked, you said that C can be changed by other people also, but the first person who will change C will do this operation.
Correct. His statement is the first person for this particular optimization, the first person that will update C applies this change. And because they hold the write latch on it, it's an atomic operation.
Otherwise, like it could have been changed.
Correct. Yes. Otherwise, it could be changed. Yes. Okay. Awesome. All right. So let's finish up. So hopefully, I've convinced you that you want to do this latching stuff, but it's notoriously hard to do, right? I've glossed over the sibling pointers, how to keep those in sync. That's a whole nother bag of we don't want to talk about. That's super tricky. But again, as I said, the good news is that because it's super hard, and if you can do this, people pay you a lot of money to do this. In practice, I would say that there's actually surprisingly, I mean, there's a bunch of concurrent data structure libraries that are out there. The Intel thread building blocks is one of them. Facebook's Folly. So in general, for low-level things like internal hash tables and things like that aren't being used as part of doing query processing and storing data as an index, off-the-shelf stuff is probably good enough. All the commercial systems all the high-end systems roll their own data structures for these things. But for table indexes, I think that building a data structure that's specific to your database system is super important, because then you can tailor it towards whatever your target operating environment is. So the other thing I'll point out too is, although we talked a little bit about hash tables, we spent most of our time talking about B+ trees. But the core ideas that I've talked about, like making sure threads are always going in one direction to avoid deadlocks, killing yourself right away if you do encounter a deadlock, maybe optimistically assuming that you're not going to have to do modifications to the structure, and therefore taking a fast path first. All of these techniques are reused all throughout computer science and data and systems in general. So it's not just B+ trees. These techniques are applicable everywhere. Okay? All right, so any questions about what we talked about so far today? All right, so the good news is that next class, we can finally start talking about how to execute queries. We know how to store them, we know how to index them, and now let's talk about actually how do you run queries on top of them and produce results.